Donc, maman, Koya numa, koya numa. Hola, first note. Allo, pour connaître space. If I know,
Hello. Hello. Good morning to you all. Good morning, class.
Good morning.
Good morning, sir.
Good morning, sir.
All right. My name is Dr. Justice Ado, and I'm the one who is going to facilitate this course via the online medium, and as well as the course coordinator who will be examining you on this course. Because this is our first meeting, please, I will want us to give ourselves some little time so that all your colleagues can join before we begin. I don't want to leave anybody behind, okay? Because if we start and they join in, they might not get the concepts that I'll be introducing you to this morning. So in view of that, it is now 7:10, but I'm giving additional 10 minutes, okay? So by 7:20, I'll kickstart and then we move. Until then, please make sure you mute yourself. Those of you who are on your mic, mute yourself so that you don't create any kind of feedback at the background. Thank you, and I'll get back to you soon.
Perfect. It's nice.
Who is on? Have I win? No, number I'm not sure. Eh, yeah, pastor, pastor, Abari. Bahabi Charles, Bahabi Charles. Ma Odubo.
Good morning once again.
Good morning, sir.
Good morning, sir. Good morning.
Good
Good
morning.
morning.
So
Sir.
Good
when
morning, sir.
it was time, and then I was introducing myself, I think I had about 40 people online, and then I told the class that because this is our first meeting, we need to wait for the others. And now the number is now 98.
Ah,
So what it means is that it's a large class, and I'm happy we have everybody on board. I really don't know whether the others who are still struggling to join. I guess at this point we can proceed, and I'm sure with time they would also join the class. Please, I will want to, before the official start of the class, I will want to give some information out, and then maybe if someone has a question or a concern, the person can raise it, and I can kickstart. The first point is that this is an online class in which you have all joined from different environments, and we are all online
Doc,
here.
please check your microphone for us. We are not getting what you're saying. The volume's too down.
For that reason, can you hear? Is it better? Is it better?
Yes, please.
Yes, please.
For that reason, let's take note of the following. I want everybody to mute his or her speaker now. Everybody, mute your speaker now. I don't want to mention names. Christopher, mute yourself. Everybody should mute his or herself now. And please, throughout the lecture, make sure you are muted. You only will be given an opportunity to unmute yourself when you have a question or a contribution to make. By that, you cannot just even jump in and talk. So if you look at your Google Meet, bottom down there, there is a portion that is showing the hand. So you click on that symbol and then you raise your hand. Now, when you raise your hand, I will see from here, and I will then call your name before you unmute yourself and then ask your question or your contribution. For those who have on their videos, there's no problem with that. But please kindly ensure that so far as you have on your video, the whole world see you, not just only your face, but your background. And as a matter of fact, make sure that the environment you are not going to display any unwholesome images for us to see. So make sure that the environment you are is that which wouldn't create a problem for you to publish or let people see some unwholesome pictures or videos. The third point is that this lecture And of course, all subsequent lectures are being recorded by the e-learning unit of the College of Distance Education running this program. In view of that, if you come in late or you join in late and you seem not to understand a particular concept which has already been touched on, please, you do not draw us back, because we have very limited time to cover a lot. So for such persons, if you tell me you are confused, you don't understand, I should go back. No, rather, through your course rep, get the recorded lecture, and then you later can watch and then maybe get understanding from there. I still have some people who have their mic on in T-Prince. Now, if it keeps on that some people are going to disturb the class, they are going to create noise, I will take note of your name and you'll be penalized for that. So those of you who still have your mic on in T-Prince, some people are in the car, some people are in a noisy environment, and they wouldn't even off or mute themselves, and they will be creating a lot of inconveniences for us. I will be having time, and then I'll be writing the names down. I will definitely penalize such persons. So please advise your colleagues. In T-Prince, only mute yourself. All right, I've muted him. Please, I'm begging you, let's make this online facilitation trouble-free by adhering to these little informations I have sent across. At this stage, since this is our first meeting, we should have known ourselves, but then time wouldn't permit. I will introduce myself again. I'm Dr. Justice Ado. I will be the one who will facilitate the online lesson for CHE 108D, Introduction to Organic Chemistry. And definitely, I am also the same person who is the course coordinator, and will be examining you at the end of the block. In the course of the lecture, I did this morning share the lecture slides for this morning with you on your page. But then in the course of the lecture or after each lecture, there might be some other materials, learning materials that will facilitate and help you with your revision, which I will be giving at time intervals, either through your course rep or on the WhatsApp platform. We are all captured. And so you can make use of that information to help you. Thank you very much. So, Introduction to Organic Chemistry is actually a course which, per the name, is not detailed. When I say it's not detailed, it just deals with the preliminary information regarding organic chemistry. And most of the topics, it is assumed that if you have done science, and of course, you have done chemistry at the secondary school level, then you should have been very conversant with most of these topics. So more or less, it should be like a revision. Nevertheless, I know most of us might have also left the classroom for long. And so some of these things, though you might have gone through, you still will need a lot of time to get things back. So organic chemistry, and please, this is a lecture,
in as much as I'm giving you lecture slides, there are some informations which will not be on the lecture slides. You can only get them whilst I'm talking, whilst I speak. So I would advise that you also take some notes. Okay, you should have your book, you should have your notebook, you should have your pen, you should have your pencil, and then begin to capture some very, very important points which I will state or will provide, which definitely might not be captured directly on the lecture slide. I'm going to give you an introductory story about organic chemistry, and all that aspects I have not captured it on the lecture slide because the introductory aspects you will be doing practicals on it, and then I'll be giving some practical manual which has those informations captured. So on your own you can be putting down some points, but when you get the practical manual, it gives you detailed information there. So when we say organic chemistry, what does it mean? Organic chemistry simply means the learning or the study of organic compounds relating to their behavior, their physical properties, and their chemical properties. It relates to the learning of organic compounds in terms of their physical properties, their chemical properties, and their behavior. So what it means is that this course is going to let us know organic compounds. So what then are organic compounds? What then are organic compounds? If I may ask, anybody to want to give us some information about what he or she knows about organic compounds? Yes, anyone? Have you heard of organic compounds before? Okay, Jefta.
Okay, thank you, Doc. So my understanding of organic compounds are that they are large class of chemical compounds in which one or more atoms of carbon, they have covalent bonding with atoms of other elements, and those elements could be hydrogen, oxygen, or nitrogen.
Okay. Anyone to add up? Anybody? What are organic compounds? Because that's what we are going to learn. So we need to know what they are. This course is about the study of organic compounds. So what are organic compounds? Yes, Ebenezer. Ebenezer, unmute yourself and tell us what you think.
Thank you. And so when you are talking of organic compounds are carbon-based compounds, usually containing CH bonds. And they are often combined with elements like oxygen, nitrogen, and some of the halogens.
All right, thank you. That's right. So you could see that the first two informations given about organic compounds basically talk about carbon compounds. What it means is that the backbone of organic compounds rests on what? Carbon. Okay, so
that's my
Sarah, please mute yourself. So I think the two of you are right. Then if I'm to ask you to name some examples of organic compounds, I'm sure we can mention a lot. Just to refresh our mind, I want 1 or 2 or 3 of you to mention at least 1 or 2 examples of any known organic compound they know. Any known. Yeah, James.
CH4.
CH4. And
Yes,
what
please.
is the
Methane
what is the
gas.
name? What is the name?
Methane
CH4, what is
gas.
the name?
Methane gas.
Methane gas. Good. Methane gas. Yes, Sefa Jafta.
So sugar.
Sugar. Yes, you are right. Sugar. And I'm sure we all know sugar. Sugar simply means what? Glucose. Okay. And glucose contains carbon, hydrogen, oxygen. Great. Yes, Emilia. Emilia. Your hand is up. William. Just give an example. Those whose hands are up.
Hello, sir.
Yes.
Ethanol.
Ethanol. Yes. Ethanol is an organic compound because it contains carbon, hydrogen, oxygen. Great. Let me take the last person. Anyone? Anyone?
Acetic acid.
Acetic acid. Great. Acetic acid is also an organic compound. It contains carbon, hydrogen, oxygen. So we could give more and more and more. But then the examples you are giving, I asked myself, have you seen them before? Because just immediate and just around you, there are a number of organic compounds that you can see. So I was expecting you to mention types or examples that are so close to you. Okay. Yes, James. All right. So oil, cooking oil, the soap that you bath with, okay, they are all organic compounds. Okay. The polythene, the plastics, the plastic bowls, they are all organic compounds. So if you look at your immediate surroundings, virtually everything that you see around you, in one way or the other, is made up of what? An organic compound, or it is an organic compound. The plants, the trees we see around us, the animals, they are all what? Made up of what? Organic compounds. In fact, the human blood, which we know contains hemoglobin, that has a high affinity for oxygen. Hemoglobin itself is an organic compound. The DNA is an organic compound. The RNA is an organic compound. So when we talk about organic compounds, we have millions and millions of these compounds all around us. But then, in defining organic compounds, we are also quick to say that, yes, they are compounds of carbon. Yes, they should contain carbon, but then there is an exception. And the exception is that the oxides of carbon and the carbonate of carbon are not organic compounds. Example, carbon monoxide, CO, and carbon dioxide, CO2. These two contains carbon, but they are not organic compounds. Why? Because they are oxides of carbon. So you cannot classify carbon dioxide or carbon monoxide as an organic compound, even though they contain carbon. Now with the carbonate and then the bicarbonate, we have examples like sodium carbonate, potassium carbonate, calcium carbonate, sodium bicarbonate, potassium bicarbonate. These ones, though they contain carbon, but we are also saying that the carbonate and then the bicarbonate of carbon are not classified as organic compounds. So if in an exams, I give you a question like, which of the following is not an organic compound? And then I give you ethanol, I give you pentane, I give you calcium carbonate, and then I give you glucose. They all contain carbon, but then the calcium carbonate option is the wrong option, or is the compound that is not organic compound, because it is a carbonate of what? Carbon. And I'm sure this is clear. Now, there is something organic compounds have been associated with all this while. When we say organic, something rings, something must ring. You know, sometimes people are going to buy food and they'll say that, oh, this food is organic. I prefer organic based food. Oh, this particular product is organic. When we say that, what does that imply? When we say that, what does that imply?
Hello, sir.
Yes. Please, those who
First
earlier
of-
on, if you earlier on raise your hand, you can put it down so that if I ask a new question, I will know those who have still raised their hand. Yes,
hello,
please
sir.
go ahead.
So back
Justice, go ahead.
back to the question. I think it's because it's mainly natural from plant and animal source. Mainly natural. It doesn't have any synthetic
Okay, so first,
component added to it. Hello.
Okay, so first is saying that when we say a product is organic, or when we say, oh, we want an organic food, then it means that it is of a natural source, either from a plant or animal source, without any synthetic, component. So whenever the word organic comes in, you are referring to what? Natural source. It's not man-made. The thing is natural, okay? And so I think that is it. So beginning and in the early 18th century, organic compounds were said to come from only plant and then animal source. So what it means is that anything that does not come from plant or animal source was not classified as what? Organic. Everything organic was seen to come from either plant or what? Animal source. Now, this is what was known and was believed for a long period of time. So if I'm tracing any organic compound, maybe I can get methanol from what? Ants. So it means that the ant is an animal and it's a natural source where I can get my methanol. If I want to get some organic compound from a plant, I go and get the plant and then extract that organic compound. So that was basically what the understanding of organic compounds in terms of their sources was with us. But then this particular idea is what we refer to as what? The vital force theory. The vital force theory. Please take notes. The vital force theory. And this theory, as suggested by Berzelius, somewhere in 1807, indicated that organic compounds were always obtained from organisms, either animal or plants. Always. So anything organic compound always is obtained from an organism, either an animal or a plant. And that is how the name organic, okay, was derived from what? Organism. So when you say organic compound, the organic compound was derived from an organism, that is either a plant or an animal. So when you say organic, we mean from a living or natural source. So this concept is what we refer to as what? The vital force theory. Vital force theory. This information I'm giving you is not captured on the slide. So please put something somewhere and you go and read more on it. Now, at a point, we had one chemist who then decided to do some work, which later became out clear that the vital force theory cannot be accepted anymore. And that particular scientist was able to use inorganic materials, ammonium cyanate, to produce an organic compound in the lab through synthetic means. So ammonium cyanate is inorganic, but urea, and I'm sure you all know urea. Urea is an organic compound found in the urine of animals. So here we are, this scientist was able to use inorganic materials, stay in the lab, and was able to produce an organic compound. If that is the case, then it means that it goes a long way to disprove the concept that anything organic should come from an animal or a plant source. Because now he has been able to produce an organic compound which is not from an animal or a plant source, but then in the lab. So from there, we decided to revise our knowledge and then our understanding and our definition of what organic compounds. You can no more describe or define organic compounds as compounds that are only from organisms or from animal or plant source. Now, as we speak right now, we have thousands of organic compounds being synthesized in the lab. We don't get them from the plants, we don't get them from the animal. But then chemists are in the lab currently, and every second, every minute, every hour, we have over thousands of what organic compounds being synthesized or being prepared. So the vital force theory you should know, but then you should also know that the vital force theory is no more accepted in the description of what organic compounds in terms of their source. Now, the next point is, I'm telling a story. Okay, all that I'm saying is a story. By the time we are done with the course, I'm sure you appreciate the story I'm telling you. It's a Kwaku analysis story. Now, organic compounds, whether from animal or plant source, they always exist as mixtures. They always exist as what? Mixtures. So if I'm to give this kind of illustration, when I was growing up in the village with my grandmother, anytime I had fever, she wouldn't take me to the hospital. Rather, she would just go and get some neem leaves. And I'm sure we all know the neem plant. She would go and get the neem leaves, boil it hot, then let me sit on a stool, then with the hot, solution, the what do you call it? The vapor that is coming out, she will cover me with a blanket or a cloth, and then my whole body gets exposed to the vapor for some minutes. And when it's done, you see me sweating. I will sweat for some time, and then I'll go and bath. In some cases, the boy leaves. The solution, she'll even pour some for me to drink when she realizes that the situation is, at an advanced stage. And I do that 1 day, 2 days, the third day, and then my malaria or fever is gone. I don't go to hospital. The question now I have been asking myself, or at a point I was asking myself, which those times I didn't ask because I didn't really understand what my grandmother was doing. But then what she was doing was purely science, and she was doing was purely chemistry. But then I also even want to know whether she really herself knows that what she was doing was science, and of course chemistry. The neem tree contains organic compounds, and these organic compounds are medicinal, and they have these properties against the fever condition. So when they give it to you, some of the organic compounds, because they are highly volatile, were exposed to you whilst you inhale. Okay. And then when you take some of the solutions too and you drink, they get into your system, and due to their medicinal properties, you get healed. So it's because the neem tree, the neem leaves, contains what? Organic compounds. Recently, research have indicated that the organic compound that is found in neem tree commonly is the azidaractin. I don't know whether you've heard of it. It's the azidaractin. And this azidaractin, we have azidaractin A, B, C, D, different types. And they are said to be predominantly responsible for the cure of the malaria or fever when you take it. Currently, we still rely on the neem to manage fever conditions. And that tells you the consistency the plant has. But all that I want to establish here by telling you this story is that if you take the neem leaf or the neem plant, it is not only one compound that is there. It is not just only 2 or 3 organic compounds that are there. There are hundreds and a lot of organic compounds in there. So when you boil it or you heat it, you are not only bringing one organic compound out, but you are bringing a lot of organic compounds out. But then, mind you, it is not all the compounds that is in the plant are medicinal. Some are also toxic. Some are harmful. And then they are the medicinal or the good ones too. But then the question is that when you boil it, you are extracting, you are bringing all of them out. So my earlier statement is that organic compounds exist as what? Mixtures. Organic compounds exist as what? Mixtures. And I'm sure we all know what a mixture is. Okay. We all know what a mixture is. So if the organic compounds exist as mixtures, then how do we separate them? How do we purify them? Because in the mixture system, what it means is that each component of the mixture is not pure. Each component of the mixture is not pure. Because in terms of purity, if you pick any component of the mixture, the other components are serving as what? An impurity to it. So mixtures predominantly, or mixtures are impure. And so if they are not pure, how do you purify them? So that leads us to the methods of purification of organic compounds. The methods of purification of organic compounds. There are a number of them. I'm going to touch briefly because, like I said, this is just the introduction, and these aspects that I'm talking about, I will later give you the practical manual, which gives you a detailed information about them, so that all that I'm saying, you will see that they are all in there. That will serve as a revision for you. One of the methods of purification is distillation. Now, distillation, the concept is you apply heat, and of course, distillation is only used for what? Organic liquids. If the organic compound is a liquid, then you can use distillation, because distillation actually operates on the concept of what? Boiling points. Okay, you heat the liquid, you boil it, and then at its boiling point, the liquid turns to vapor. So if you have a mixture of what? Organic liquids, then you can only use distillation to separate them, because the individual components in the liquid mixture, they all might have their specific boiling point. So when you start heating, if liquid A, which boils at 60 degrees Celsius, when that temperature gets to 60 degrees Celsius, it is only the liquid A that will change to vapor. And then when it changes to vapor, it passes through the condenser, and then you condense the vapor back to liquid and you collect it. By the time the temperature will rise to maybe the next component's boiling point, which is, let's say, 80, from 60 to 80, by that time, the one that boils at 60, you have collected all already. Then the one that boils at 82 will change to vapor, and that one to get condensed, and so on and so forth. So because the individual component of the liquid mixture have different boiling points, they will be converted to vapor at different temperatures and then condensed back. In so doing, you can collect them individually and in their pure form. This method is only applicable for organic liquids. If the organic compound is a solid, you cannot use distillation. There are a number of distillation methods, but as far as this course is concerned, and of course you do practicals on it, we have the 4 basic distillation methods: simple distillation, fractional distillation, steam distillation, and vacuum distillation, which we also call distillation under reduced pressure. Simple distillation, fractional distillation, steam distillation, and distillation under reduced pressure or vacuum distillation. These are the 4 basic ones which I want you all to know, because I'll ask a question on it. I can ask you to list the 4 basic distillation methods, and you should be able to list all these 4. But then having different types of distillation means that they might actually be applicable at different instances. So the question then is, at what point will you have to apply simple distillation? At what point will you have to apply fractional? At what point will you have to apply steam and then vacuum? So again, you need to know the differences. At this point, I will want anybody who has a little knowledge about any of these types of distillation to briefly tell us what he or she knows. The 4 types of distillation I've mentioned.
Hello, sir.
Yes.
Festus.
Yeah, first let's
Okay,
go ahead.
so with a simple distillation, it's normally used on substances with wide boiling points, wide
Okay.
range of boiling points. That is the simple distillation.
Okay. That is right. Can you give a specific example? Like two different.
Um, uh, for, yeah, like for instance, palm wine, separating alcohol from the palm wine. When you collect the palm wine, then you want to separate them. That's the water from the palm wine. I think alcohol boils at 78, whilst water boils at 100. The boiling points are wide a bit.
Okay. So
So that one normally is used.
I guess this is something that you yourself you can even do. So one of these days I'll let you get me some palm wine here down here in Cape Coast. Okay. Yeah. Anyway, yeah, you are right. So here the 2 or 3 or more liquids that are in a mixture and you want to separate. Okay. When you realize that they have very wide difference in boiling point, that is, if you take each one of them's boiling point and you compare with the other, there's a wide difference. One of them maybe boils at 60, the other one boils at 70, the next one boils at 80, the other boils at 100. So if you look at the difference, it's over 10 degrees. Okay, sorry, 10 degrees Celsius. In such a situation, you can use simple distillation to separate them and purify them. Because simple distillation is cheap, easier to handle. So he's right. Can we get another about the other types of distillation? I see, is it Frank Paddy?
Yes, Doc.
Yes.
Okay, please, I'll speak on the fractional distillation.
All right.
Okay. I think that is used to separate components of a mixture with very close boiling points. For instance, the separation of the various fractions of crude oil.
All right. So, Frank, you are very right. And then the example you've given is very, very, very appropriate. Okay. You see, the crude oil has a number of organic compound components. Okay. You have petrol, you have diesel, you have kerosene, you have naphtha, you have, a whole lot. And the numerous components in the crude oil are such that their individual boiling points are very closely related and closely, to each other. A difference of maybe 1 degree Celsius or even 2 degrees Celsius. So in such a situation, if you are to use simple distillation in separating or purifying, you might end up getting one of the components still mixed up with the other, and you might not have achieved your aim. So you go for fractional distillation, and he's right that it can be used to separate the crude oil mixture. But then what is so unique about the fractional distillation is that it makes use of what we call the fractionating column, which is not part of the distillation setup. In the fractional distillation setup, there's a fractionating column component, and the fractionating column also itself help us to separate, components. So beyond the boiling point difference, within the fractionating column, which is embedded with what beats, okay, over there too, there is what multiple separation of components taking place. So no matter how close the boiling point is, you still end up collecting them at different times and then condensing them in their pure form. Good. So please, those who have raised your hand and then you have talked, or you can lower your hand. But I can see Andema Pitha Jr., Jeff Tasifa, if you want to pick on the steam and then the vacuum distillation. You can go
Good
ahead.
morning, Doc.
Good morning.
Please, this is Peter.
Yes.
I would like to speak on the vacuum distillation.
Yeah.
Usually, the vacuum distillation is used to separate components by reducing their pressures. Usually, the reduction of the pressures enables you to separate mixtures or two components that have a high boiling point. So, for example,
so are you not talking about steam rather? Your information sits well with me on steam distillation. Okay. Yes, for the steam distillation, usually it is used to separate or extract, essential oils or organic oils. These oils, they have very high boiling point.
Yeah.
So you might not necessarily be able to even provide the energy that can be used to offset that high boiling point. So you then will want to do that under the water vapor, which is 100 degrees. Okay. So though their boiling points are over 100 degrees, you will still separate them at that temperature. So under steam, all those oils get extracted and separated. Okay. So it works, your definition works with steam distillation. Okay. And those of you who the orange peel, okay, the orange that we eat, the peel, the cover, you see when you squeeze it, it contains some oil. Okay, there's some liquid that comes out. Those things are all organic oils, and some of them have high boiling points. So you can use steam distillation to purify or separate such. But when it comes to the vacuum, okay, or the distillation under reduced pressure, this one does not reside solely on temperature because the compounds involved easily decompose when you apply higher heat. Okay, you see, we have some organic compounds, the little heat you expose them to, you end up destroying them. So if you use simple distillation or fractional distillation or steam distillation, by the time you finish separating them, you have even ended up destroying them. So for such compounds, we prefer to use the vacuum distillation or the distillation under reduced pressure. So what it means is that the focus is not going to be on temperature, which will end up destroying them. The focus is going to be on what? Applying pressure rather. Okay, so that at much lower temperature, you can still end up, purifying or separating such organic compounds. So usually for highly volatile compounds, very unstable organic compounds, we prefer to use the distillation under reduced pressure or vacuum distillation. So this is one of the methods that can be used to purify organic compounds, specifically organic liquids. And these are the 4 different types, and then we have really touched briefly on them. When you get the materials, you'll be doing practicals on all this. So not even the theory, the practicals that you'll be doing, you do practicals on all this, and so you get more insight. Another method.
Hello, sir.
Yes.
Hello, Doc.
Yeah, go ahead.
Please, can we have a typical example of substances that can be separated using the vacuum system, the vacuum method?
Yeah, there are a number of them. So a minute. There are a number of such compounds, okay? And in fact, if you take even the let me say the earlier members of the alkane family, okay, alkanes with carbon 1, they themselves, they exist as gases, okay, and some of them, even though they are liquids, but then they easily decompose. So those early members of the hydrocarbons can be used you can use the vacuum distillation in purifying them. All right.
Okay, thanks.
Any other person who has any information to add?
Yes, Doc.
Yes.
I once read that they are used to separate, like you mentioned, high sensitive materials like pharmaceuticals and essential oils. I don't know if you can
Yes.
also remember this.
Yes, that is also true because some of the essential oils are highly volatile. Okay. In fact, if you enter any chemistry lab and then you have some of these essential oils, as soon as you enter the lab, you start smelling them. Even at room temperature, okay, they are already volatile. So you can even be smelling them. So for such a compound, if it is impure and you are purifying it, even at room temperature, it is already going, it is escaping. So if you go and apply it again, you end up losing it or destroying it altogether. Even tertiary amines, okay, amines, we have different types. The organic chemistry you'll be doing in the semester 2, I'll handle you and we'll deal with the amines. The tertiary amines are also a class of organic compounds that we normally, if they are impure, we normally use the vacuum distillation. Okay, tertiary amines, because when you apply a little heat, they form something else, alkenes and then secondary amines. So you wouldn't want to change them to those components. Then you don't have to apply heat. You have to use the vacuum distillation. Thank you. If there's any other thing, if not, we move on. All right. So the lecture is from 7 o'clock all the way to 11, right? So we will, when we get to a point, we'll break for about 5-10 minutes and then take some rest or some small distance, then we come back. All right. But even during that period, you still have to stay online. Don't go offline. Now, the other method of purification we want to look at is crystallization and recrystallization. Crystallization and recrystallization. Now, when you have an organic solid and it is impure and you want to purify it, then you cannot use distillation because solids do not boil. So in the case of the impure solid, then one of the best methods to use is to use crystallization in purifying it. Now, the concept of crystallization is just formation of what? Crystals of organic solids. So you will need to, first of all, select or get an appropriate or suitable solvent. Now, that appropriate or suitable solvent we are referring to here means that at the boiling point of that solvent, this impure organic solid should be able to dissolve, leaving behind the impurities. So at the boiling point of the organic liquid, the impurity should be insoluble, but then the organic compound, the impure organic compound, should dissolve. And that's what we mean by a suitable or appropriate solvent. So the first is what you do. You select an appropriate or a suitable solvent. Then you dissolve this impure solid at the boiling point of the liquid. When you do that, then you filter hot the dissolved solution. And the filtration technique to use here is what we call the gravity filtration. The gravity filtration. Here you need a funnel, tester funnel. I'm sure you know tester funnel. Then you will need a fluted filter paper. Okay, and I'm sure you also know a filter paper. But when we say a fluted filter paper, what it means is that it is this the special folding of the filter paper. You fold it, overlap, so that it will have different, compartments. That is what we call the fluted filter paper. Now, when you fold the filter paper in that manner, it provides a large surface area to facilitate the filtration process. So the fluted filter paper is then inserted into the funnel. Then you pour your hot solution on it and then filter. What it means is that the compound of interest, the dissolved compound of interest, comes out with the filtrate. And the impurities, the insoluble impurities, the solid material is left on top of the filter paper. So the insoluble impurities, which is making your compound impure, they don't get dissolved and they don't accompany the filtrate. They are left on the filter paper. By the name gravity filtration, it means when you pour everything on the filter paper under the force of gravity, you get the filtrate, coming down, and then you have your filtrate. Now, when you get the filtrate, how then do you get your solid, your organic solid back, the crystals back? What it means is that you need to cool the solution because you already bought the solvent. So the first thing is that cool the solvent, cool the solution to room temperature. And from the boiling point of the liquid to the room temperature during the cooling process, you expect to see the crystals formation of your purified compound. And that crystal formation is what we call crystallization. You are forming crystals, solid crystals, crystallization. When you form the crystals in the solvent, then you go again to another form of filtration. The first one was gravity filtration, but now this second one is called the suction filtration. Suction filtration. Now, suction filtration operates under pressure. So over there, you don't use the tester funnel. You don't use a fluted filter paper. What you use here is what we call a Buckner funnel. Buckner funnel. So please, when you go into any chemistry lab, you should know the difference between a tester funnel and then what? A Buckner funnel. Now, in the Buckner funnel, you connect it to what? A pressure, what do you call it? Source. Okay. So the whole system is a Buckner system, suction system, but then it operates under pressure. So you connect it to a pump, okay, a pressure pump. Then you line the Buckner funnel with what? A filter paper. This one you don't fold it, so it's not fluted. You just lie in there. Then you pour the crystal that has formed in the solution. You pour it on the Buckner funnel with a filter paper. Then the crystals that has formed will be left on the filter paper, whilst the solvent that you use for the purification will be drained down. Now, when you are done, you wash your crystals with more solvent to make sure that it removes any trace of what impurities. And after that, the next stage is that you have to dry your crystals that has formed, because even though you have used the suction pump to suck all the solvent, there will still be traces of solvent in the crystals, making it moist. So you have to dry your purified crystals. And one way of doing it so that you don't get it contaminated again is to dry it in a desiccator. A desiccator is a system which contains silica gel, which is a drying reagent. And so when you put that purified sample in there, the silica gel absorbs all the moisture from it so that the crystal form becomes very dry. And when you are done drying the solid, you then will have to check whether the compound that you have purified is indeed pure. Now, the steps that I've given you about crystallization, if you have a colored impurity, okay, if you have a colored impurity, then it means that it will still stay because colored impurities cannot be removed with the filtration systems. So in such a situation, you need what we call activated carbon or activated charcoal. Now, activated carbon or activated charcoal has some kind of adsorption properties, which when you add it to the solution, it will take away all colored impurities from the compound before you go ahead and filter. Another point I want to raise, if before any question on the crystallization too, is that sometimes when you are cooling the whole solution after you have filtered and you are cooling it for the crystals to form, you realize that the crystals might not be forming. There will be difficulty in the crystal formation. In so doing, there are some techniques we need to employ to be able to what? Cause the crystal formation. And I'll give you 3 of them. One of them is you can put the solution in the fridge or in an ice, because you know the room temperature is around 28. So if at that temperature the crystals is not forming, you know the fridge, sometimes the temperature can go as low as 4 degrees or even minus degrees. So when you put it in the freezer, you then will see that the crystal formation will be taking place. That is one. The second method is you can get a glass rod, stirring rod. Now the container in which the solution is, which you expect it to have to form the crystals, use the glass rod to scratch the side or the bottom of the container. So scratching the inner walls or the bottom of the container would facilitate the crystal formation. The third one is what we call seeding. Seeding the solution. SEEDING. Seeding, or we say to seed the solution. Now, to seed the solution here simply means that, let's say the compound that is impure and you are purifying, let's say it is benzoic acid, that is not pure and you want to purify. Then we are saying that if the crystals are not forming, then get a small amount of the pure form of the sample under study. In this case, the compound that you are purifying, okay, if it is benzoic acid, get a small amount of the pure form of it and add it to the solution. As soon as you do that, it will go and then aggregate all the benzoic acid molecules in the solution, and then the crystals will start forming. So these 3 techniques is employed when there's difficulty in crystal formation. Now, when you have gone through all this process, from what I've just described, and then it comes out that the compound is still not pure, then it means you have to repeat the whole process again. The whole process of crystallization, you have to repeat it. And that's what we call recrystallization. So the process that I've described is crystallization. But we are saying that after going through all the steps involved in crystallization, and then the crystal that comes out is still not pure, you need to go back and repeat the process. So you going back, then we refer to that one as what? Recrystallization. So know the difference between crystallization and recrystallization. So that is the second method of purification of organic compound. Any question on that? If not, I continue.
Doc, I have a question. My hand is up.
Yes, go ahead.
So I'm trying to find out that having gone through all of these processes with the crystallization, the recrystallization, how do you assess the purity of the compound you get?
Yeah, so that's the next stage we'll be going. I really wanted to touch on all the methods of purification first. And when you are going through any of these methods of purification, you don't just assume that the compound is not pure. You should actually go ahead and use certain techniques to ascertain or to check before you can know it is pure or it's not pure. So we'll get to that point very soon. Like I said, it's a story I'm telling you, so just follow the story. Any other question?
Hello, Doc.
Yes.
In fact, I'm enjoying the lesson, and I can see that there are a lot of wonders that happens in the chemistry lab. Please, with the scratching method, wonderful. And what is the chemistry behind it? That's scratching the bottle with a rod and
okay,
not even stirring the solution or the substance, but rather scratching it. So I'm imagining how.
Okay, so when you read more about crystal formation, okay, you know, we are talking about organic solid, okay, and then the compound is made up of crystals or the molecules. Do you understand? So when you say sugar, is that right? The sugar molecules are numerous, okay. So it is when they aggregate, when they come together. Do you understand? Then you see them forming like a large, solid with time. So beginning in the solution, in the whole solution, and at the boiling point, these molecules they are all now scattered. At that point, they have acquired some internal energy. So they are just moving randomly in the solution. So that will not allow them to aggregate or come together and form the crystals. So in cooling, if you are finished cooling, but still their energy is still high, okay, the particles are there, but they are not able to come together to cause the crystal formation. So now, when you start scratching, okay, it's like you are disturbing their current system. So whatever the rod is going to be scratching, either the side or the bottom, that will cause their attention to be moving towards that spot. So when you have multiples of particles moving towards one particular spot, then when they get there, there's what we call the crystal lattice. Okay, similar molecules get closer and then they form some kind of bond. Okay, there's some form of attraction and then they start aggregating as solid crystals. And as for the lecture, yes, I know you enjoy my lectures, and I hope you also will be enjoying my exams. Any other question?
Yeah, Doc, please, any examples of crystallization and recrystallization?
Okay, so if I know benzoic acid is a people are laughing because I said I hope you enjoy my exams. Yes, at the end of the day, there are two things. I'll come to your question. I always love to impart knowledge, and when my students get knowledge, I'm happy. You know, when you show to me that you are getting knowledge, I'm happy. That is one. And then because it's a program, you definitely have to also pass the exams, and that is where um I was talking about. But you'll be fine. You'll be fine. Okay. That's why I said I'll be giving you review questions and then tutorial questions as a guide, and you do you can ask those who have done the cohort 1, cohort 2. They will tell you. All right. So back to your question, which has to do with we're asking examples of like this crystallization, recrystallization. So I have benzoic acid. Benzoic acid is what? White crystalline solid. Okay. Then maybe in the lab, accidentally, you might have introduced sand, or you might have introduced another solid, another material, okay, to it. So now you want to get back your benzoic acid pure. You want to purify your benzoic acid pure, okay? So first of all, there should be a solvent, a suitable solvent that can dissolve the whole benzoic acid at its boiling point. But then that sand, that impurity, still will remain what? Insoluble. Then you filter, okay? So as for the example, it could be any known organic solid, which maybe it gets other materials into it, which then becomes an impurity. And then you have to find a way of what? Taking away that impurity. So as for that examples, I mean, you can have a lot. Can we continue, please? We still have some questions. I see Azuma Peter and Bashir Adamu. I don't know whether you have a question to ask.
Sir, please. Festus. Sir, please, so kindly use the example that you stated right now, benzoic acid plus sand. Let it be that you are going to use this crystallization method. So kindly take us through example. You are having benzoic acid plus sand. So it's like I want you to.
I will do that. But then, like I said, you also be doing my practicals as well for this course. You know, every organic course has a practical component. Okay, so what I've just done is that most of these techniques that I'm telling you, I have developed a practicals on it for you to go and do them in the lab. So you definitely will be taking through all this in the lab. But yes, still, if you want me to go ahead and do something like that, yes. So I would then we'll go for methanol. Okay. Now, when I use methanol, then I'll boil the solution. Okay. So at the boiling point of methanol, the benzoic acid will dissolve, but then the sand will remain insoluble. Okay. Then I will filter using gravity filtration. So I will have my container, my tester funnel, then my fluted filter paper. Put the filter paper inside the funnel. And because the benzoic acid at the boiling point of methanol is already dissolved, you can't see it. It is part of the solution. But then the sand is insoluble in methanol. It will be there as what? Particles. Then I'll pour the solution on the filter paper. What it means is that all the sand, all the particles, all the impurities, which are insoluble, will be left on the filter paper. And the filtrate, which is coming out, is the methanol and then the dissolved benzoic acid. So now I have managed to take away my impurity on the filter paper. And at that point is what I'm saying, that even if there is also a colored impurity, then I will add activated charcoal, or I'll add activated carbon, which we also call it the norate, so that one too will go and remove all the colored impurities before I do the filtration. Now, after filtering, my benzoic acid is still dissolved in the methanol. So how do I get the benzoic acid, which is solid, to form back a solid for me to get it? That is what we have to go by the cooling. So I have to cool the solution because I heated the methanol. So I have to cool it to room temperature. Now, in the cooling process, the benzoic acid will start forming the solid crystals, will start forming. That is what I'm saying, that if it happens that the solid is not forming at room temperature, then you can apply this method of scratching, seeding, or putting it in what? Ice block or fridge to hasten the crystallization. So when you cool and then the crystals form, again, the methanol that is formed with the crystals should also be removed. And to remove the solvent, we don't use gravity filtration, but we use suction filtration. So now I have my suction pump or my suction setup. Then I pour the crystals that has formed and then the solvent all on it. Then the methanol will be filtered out, leaving the crystals on the filter paper. Okay. Then I will wash the crystals with more methanol. The idea is to remove any traces of impurities that might still be in there. After further washing, then you will see that not all the methanol solvent might have been removed. You will realize that the solid will still look a bit moist. Will have some traces of what? The solvent. So I have to dry it. Now the drying process is what I'm saying. If you leave it in an open space, there's a temptation that another sand might even, in the course of drying, some sand might even enter it again, and then to make it impure. So the best technique is drying it in the desiccator. Now the desiccator system contains an enclosed glass system having silica gel or a drying reagent. So the drying reagent in the desiccator is able to absorb, or first of all, it will saturate the desiccator and then make sure that any moisture, any liquid moisture will be absorbed from the solid. When the crystal is fully dried, then it is assumed that your benzoic acid is now pure from any sand. It's not pure from any impurity. But that one, we are saying that if you go through all this process I'm telling you, and you realize that still you could see some traces of sand or some impurities, then you have to go back and then repeat this whole process. And the repetition is what we call recrystallization. In fact, one of your colleagues asked the question, how will you know that it is pure now or it's not pure? And that's what I said, we'll be moving to that point very soon. So when we get there, I'll explain to you how you can check. So if you want me to use the benzoic acid sand impurity to describe how you purify it, this is just, but you go into the lab and then perform the experiments yourself. In fact, the course content is a lot.
Thank you very much. Thank you very much.
This is the introduction, and then the introductions will lead you to the hydrocarbons, alkanes, alkynes, and then the benzene chemistry. So we need to move a bit fast because at the end of the day, we need to cover everything before we are done. Yes, John Amaniampong. John, your hand is up, please.
Sorry, sir.
Please, if you have no question, just lower your hand. If you don't have any question, lower your hand. If you have a question, please ask.
What?
Yes, Doc.
I will ship you right now. I'm gonna come here now.
Doc.
What?
Yes.
What gun?
Yes, please. You made mention of the pistol funnel. I don't know if the dropping funnel can also be used. You made mention earlier on of the pistol funnel, and I wanted to find out if the dropping funnel can also be used in place of the pistol funnel.
What's the difference?
Well, one has a tap and the other one does not have a tap.
Yeah, so both can be used. Sometimes the one with the tap is also used to moderate or control the flow. Okay. So both can be used.
Thank you, sir.
Hello, Doc.
Yes.
Yes, please, can a mixture of salt and sand be separated using the crystallization? I think an example that I want to know.
I would say yes, but then I would say that the example you are giving, the salt you are referring to is a common salt. It's not an organic compound, so that is not my interest here. You know, the benzoic acid I give is an organic compound, so we are looking at how to purify organic compounds. Is that right? So if I ask you to give an example of a mixture that can be used, that we can use crystallization, please give examples involving organic compounds. I hope that's
okay,
clear.
Doc. Thank you. Okay, Doc.
Okay, I think we can move on. In fact, we've not started organic chemistry proper. This is just the introduction.
Doc, please,
Azuma.
my hand is up.
Oh, sorry. What's the name, please? Is it
Nima.
Tahir?
Nima. Yes, please.
Nimatu. Okay, please go ahead.
Please, Doc, can you explain the solution again for me? When you said it is highly
Okay,
difficult, yeah.
Yeah, so Nimatu, you get the recorded lecture, okay? Right?
Yes,
You'll
please.
get it. So when you watch it, you get it. All right.
Thank you.
Welcome. All right. So the other methods, I'm just mentioning them. I will explain them in detail. Another method that can be used to purify organic compounds is what we call the solvent extraction. Another one is the liquid extraction. Another one is what we call the chromatographic techniques, okay, where we have the paper chromatography, the column chromatography, and then the thin layer chromatography. These ones permit me to just mention the names because when you get the practical material, I have given enough information there that will help you. Thank you very much. Now, after going through the purification process, what shows that the compound is pure? One, if the compounds that you were purifying are liquids, then we can determine the boiling point. We can determine the boiling point to ascertain whether the purified organic liquids are pure. If the compound that you were purifying is a solid, then you can determine the melting point to ascertain whether the compound is not pure. So remember, we determine boiling point for organic liquids and we determine melting point for organic solids. Now, how does this information help us to establish the purity? For any organic compound that is pure, whether solid or liquid, its boiling or melting point range should be narrow and sharp. Should be narrow and what? Sharp. Usually, there is a difference of what? 1 to 2 degrees Celsius. Now, in determining boiling point and then melting point, we always take two values, the lower limit and then the upper limit. If in the case of a solid, the temperature at which the solid begins to melt, you record it. Then the temperature at which all the solid have changed to what? Liquid. You also record it. So melting point and boiling point determination, they are always two values, the lower and then the upper limit. So it's always a range. So if you are reporting, let's say, the melting point of an organic compound A, you can say that is what? 60 to 62 degrees. The 60 degrees is the lower limit. The 62 is what? The upper limit. Now, the difference between the range is what? 2 degrees. So we are saying that for a pure organic compound, whether it is liquid or solid, the boiling point or the melting point difference should be sharp, should be narrow. Usually, we look at 1 to 2 degrees. Then you can say that the compound is pure. If the melting point or the boiling point range is beyond that, let's say you are 5 degrees, a difference of 5 degrees or 10 degrees, that should tell you that there are still some impurities in the compound. So go back again and repeat your purification process. That is for boiling point and melting point. I hope that is clear.
Yes, sir.
Good. Now, set.
Yes, please.
Set. Please mute yourself. Where you are, you always give us a fee. Set, your background is not good at all. So please, if possible, you don't unmute yourself. Okay, you always give me a feedback here. All right. Now, I've seen a hand up, but before that, let me touch on another method that can be used to ascertain the purity. There's another one we call mixed melting point. Mixed melting point. Now, let me ask you this question. If you enter a chemistry lab right now and you see 2 containers containing a whitish substance, solid, then the bottle, they have indicated their melting point, that the one that is labeled as bottle A, the melting point is 50 degrees Celsius. Then the one that is labeled as bottle B, that one too, the melting point is also 50 degrees Celsius. The same thing. Can you say that the 2 compounds are the same because they have the same melting point? Can you say that? Because we know that the boiling point or the melting point is also a characteristic property of an organic compound. Why you say ethanol, what is the boiling point of ethanol? 78, right?
Yes.
Yes.
Yes, Doc.
Yes, sir. 78.
So what we are saying is that every organic compound that is liquid has its own unique boiling point. Every organic compound that is solid has its own unique melting point. And this I used to characterize them. So when you mention ethanol, what's the boiling point of ethanol? Well, it's 78 degrees Celsius. Okay. So if you go into a chemistry lab and you see 2 containers labeled A and B, and then their melting point written on them, this one is 50 degrees Celsius, this one is also 50 degrees Celsius, can you draw a conclusion that the 2 containers, the 2 compounds, the compounds in the 2 containers is the same thing, or they are different? Yes. Yes, Bashiru. Bashiru, unmute yourself and then give us the answer, if you know.
No, sir.
I
don't think, no, it will not be the same, sir.
Okay, you think that you cannot draw a conclusion that the 2 are the same?
Yes, sir.
Why? Because they're having the same melting point.
Maybe I could attribute it to maybe their densities too.
Okay, so you see, the densities are a different physical property. That one is not written on them for you to see. Now it is the melting point that has been written, and you can see with your eyes. So at that initial point, can you, based on the melting point, that they are the same and say they are the same or not? But I think I agree with your answer that you said you think that they are not the same. But if you are saying they are not the same, what is the reason In an example, I'll ask you.
So can I come in?
Yes, come in, please.
So my thinking is that maybe one of the bottles, the compound in there may contain impurities you may not know, which can influence the melting point to be what you see.
Okay, so that confirms the Bashiru's decision that they might not be the same, right?
Yes, Doc.
Okay. Any other person with a different view?
Hello, sir.
Yes.
For me, I think they are the same. They will be the
Okay.
same.
Okay.
One, the reason is, so far as they are, you said 2 bottles are found in the lab. So it is believed that they are in their final state, and as per their characteristics, every liquid, every substance has its own boiling or melting point. So far as they are the same, they are having the same melting point or boiling point, then probably they are the same.
Okay.
They are the same substances. So far as they are all having the same boiling point.
Okay. So thanks for your advancing your arguments. I think it makes sense. I will come in, but then let me take one more person who also want to share a view on this. Christopher Sare, Azuma Peter, Ebenezer Kenneth, Atta. I've seen your hands up.
Yeah, please, Doc. Good
Okay.
morning.
Yes.
Please, I want to talk about what you made mention that. So, if they put the substances in the 2 containers, and it happens to be white substance, what I would say is that we can also look at the color to see whether all of them bear the same color. If one is differ, then we can conclude by saying that they are not the same, though they might have the same melting point. But when we look at their appearances, or when we
Okay,
look at the characteristics,
so Peter, I had indicated that when you enter the chemistry lab, you saw 2 containers. One is labeled A and one is labeled B, and both contain the same whitish solid substance in them, and their melting point written, which is also the same, 50 degrees Celsius, 50 degrees Celsius. So the color issue too had been said that they are all white.
Okay.
So based on that, do you think they are the same or they are different?
Why we consider their melting point, they might be the same, but in terms of densities and other things, they might not be the same. Though the density might not be written on them, but when going forward to determine their densities, they might not be the same.
Okay. All right. So what I want to draw attention is the mixed melting point technique. Okay. In a situation like this, and as scientists or chemists, we don't just look at what we see in terms of labeling and then go ahead and draw a conclusion. Okay. So if we are to look at the concept of what melting point, we are saying that if a compound is not pure, it will have what a wide melting range. And if a compound is pure, you will get what a narrowed what melting range. So if you are a chemist and then you go into a lab and you see a situation like this, then the advice is that employ the mixed melting point technique. The name is what? Mixed. So what you do is that take a little amount of what is in the bottle A, then take a little amount of what is in the bottle B, okay, and mix them. Then determine the melting point of that mixture. If the 2 are actually the same because of the melting point being the same, then when you do the melting point on the mixture, that should also give you what 50 degrees Celsius. Okay. Or it should give you the same narrow range as the individual's melting point is captured. But if the compound in bottle A is different from that of bottle B, as soon as you take a little of each one and you mix, what it means is that you have mixed two different compounds. And as soon as you have mixed two different compounds, each one of them will be serving as an impurity to the other. Now, in melting point determination, what does an impurity do? Impurity always widen what? The melting range, and they also depress it. So when you mix a little amount of each and you determine the melting point of the mixture, you will realize that you will not record the 50 degrees again, but you are going to get maybe 48 to maybe 55 degrees. 48 in the sense that the melting point has been depressed from 50. Then if you look at the range, 48 to 55, the difference is what? 7 degrees. Very wide. And that will tell you that the two compounds are not the same because they are serving as what? Impurity to each other, which is causing this new melting point value that you are getting. So it is the mixed melting point technique that can help you to check or determine whether they are the same or they are not the same. You cannot just look at the data or the label and then draw a conclusion. Or you cannot look at just the physical look that they are all white, solid, and then draw that conclusion. I hope that is clear.
Yes.
Yes, sir.
Good.
Sir, please, can I ask a question?
Yes, you can.
All this thing has been occurring to me with regards to boiling point. If it is one value accepted, but if it is a range, like you said right now, 48 to 55, does it mean that it's either the substance will melt at the temperature of 48 degrees or it will melt at 55? What does that mean when we say it's a range? Does it mean that, because I know that at the end it will still give you one figure or one value. So if it's a range, and for instance you are having two liquids or a liquid which has been mixed, what will help you to know that I don't know if what I'm saying you are getting me?
I get your question clearly.
If you say something
and
is
very
a
well.
range.
I get your question clearly and very well. Now, in melting point determination, and like I said, you'll be doing this in the lab, so you should have a real feel of it. When you subject the solid to heating, okay, whichever melting point apparatus that you are using, the technique is that as soon as you see that the solid has begun to melt, that is, it is changing from solid to liquid, record that temperature. And that is what we call the lower limits. But you know, the solid do not all melt instantly. It takes some time. So the first temperature that you recorded was the beginning of the melting process. Then the second temperature is when the whole solid has completely melted. You also record that temperature. So melting point determination is always two values, a range, the lower and then the upper limit. And that is how it is reported. But you know, most books and then most literature always report either the lower or the upper limit. Do you understand? Some books will report just one of the figures, but then it is always a range. And the range that we are talking about is the lower and then the upper limit. Beginning of the melting, you record the temperature, and when the solid is completely melt, you record another temperature. And it happens within, you know, a very fast, you know, time. That is if the compound is pure. Now, if the compound is not pure and there's an impurity, you realize that after recording one of the features is that it depresses the temperature, meaning if the melting should start at 50 degrees Celsius, because of the impurity, even from 45, it will start melting. But then when it starts melting at 45, you realize that it will take a longer time for the whole solid to completely melt because of the impurities. So from 45, by the time the full solid is completely melt, you will go and read the temperature again, and then it's around 55. And from 45 to 55 is 10 degrees. The question is, why this wide difference or range? And that is what is explained by the presence of what? An impurity. Please, is it clear?
So thank you. Now I've gotten it. Thank you very much.
Great. So now the storyline is on and on and on. Okay, I'm telling a story, and so follow the storyline, because at the end of the semester you're also going to tell me a story. Now we have purified the compound, we have checked, and we say it is pure. The next question is, let's look at the whole thing. I went into the forest. I have, let me use even the cinchona tree. Okay. It's like the neem tree. It was used to manage malaria. So anytime one is sick, they go and cut the back of the cinchona tree, come and boil it, you drink, and then your malaria goes. Then the chemists sat down, they're like, what organic compound is in the cinchona tree that is responsible for the cure of the malaria? So they went in, cut the tree back, brought it to the lab, extracted all the organic compounds in there, and they realized that there were a lot of compounds there, which is a mixture. Then they went ahead and say, how do we purify it? And because the compound is solid, they say, oh, then let's use what? Crystallization, or let's use another technique. So the organic compound was extracted in a mixture, then it was separated or purified. When they finished purification, they needed to check whether the compound is pure. Then they use other melting points or mixed melting points, or we can also use refractive index and then other techniques to check. Okay. At this level, the other techniques are types that we only will leave it to the chemistry major students. Okay, here I know I'm teaching all science students, chemistry major, physics major, biology major, and all those things. But later with the chemistry major, I'll give them extra information on that. Now, after going through the method to check that the compound is pure, and you realize that, oh, this compound is pure. In the case of the cinchona tree, when they got the pure compound, and they realized that this is what is responsible for the cure of the malaria, okay, they needed to know the structure of that compound, so that we don't always go back and go and cut the back of the tree, but then we can then stay in the lab and produce more, because we know that the vital force theory was disproved when chemists started preparing organic compounds in the lab. So if we can now prepare organic compounds in the lab, and then we have seen one organic compound which is being used to cure malaria, then we need not to go and cut the tree again. We can stay in the lab and produce more. So after the pure compound has been identified and it is holding you, then you move to the next stage. The next stage is that, does the compound that you are holding contains carbon? Does it contain hydrogen? Does it contain oxygen? Does it contain nitrogen? So if it does contain all these elements, how much of each does it contain? So we have what you call the elemental analysis. Now, elemental analysis here, we have what you call the qualitative analysis and then the quantitative analysis. The qualitative analysis involves tests that can be used to check whether carbon is there, hydrogen is there, oxygen is there. Then the quantitative analysis is also a test that will tell you that, oh, if carbon is there, then this is how much carbon is there. This is how much of hydrogen is there. This is how much of oxygen is there. So with this particular course, we all need to know how to test for carbon and hydrogen, because organic compounds, we know, contains carbon. And this course, which will deal with the hydrocarbons, hydrocarbons contain carbon and hydrogen. So at least know how to test for carbon and hydrogen. This one, secondary school, integrated science, we all did it. How do we test for carbon? We know that the organic compound, when you burn it, that is when it undergoes combustion, it forms carbon dioxide gas and then water gas. Now we know that in carbon dioxide there is carbon there, and we know that in water vapor there is hydrogen there. So if you're able to test for carbon dioxide and carbon dioxide is present, that means carbon is what? Present. If you're able to test for water vapor and it's present, that means hydrogen is what? Present. How do we test for carbon dioxide? All we say is that you pass the gas through what? Lime water. And when you pass carbon dioxide through lime water, it changes the lime water to what? Milky. And that is a positive test for what? Carbon dioxide. Of course, if carbon dioxide is present, then automatically carbon is present, because carbon dioxide is what? CO2. In carbon dioxide, we have carbon. Then, how do we test for hydrogen? The water vapor, okay? The H2O contains hydrogen. So if you test for water and then water is present, then it means that hydrogen too is present. So how do we test for water? Can somebody help us?
Yes, Doc.
Yeah, go ahead.
Yes. If you are to test for water, you can use anhydrous white copper 2 sulfate, or anhydrous cobalt chloride. And so with the anhydrous white copper 2 sulfate, if it turns blue, then it confirms the presence of water. But then the cobalt chloride, which is already blue, when it turns red or pink, then there is the presence of water.
You are right. So anhydrous copper sulfate is whitish in color, very white. Now it is hygroscopic, meaning it can absorb moisture. So if you pass water vapor through anhydrous copper sulfate, which is hygroscopic and can absorb moisture, if water is there, it will absorb it. And when it does absorb it, its white color changes to what? Blue. It changes from white to blue. That tells you that water is present. And if water is present, it means hydrogen is present. And you can also use the copper chloride test, as you have said. Okay, so the information I'll be giving you later, I won't mention all here because of time factor, but then we know that you can also use the Dumas test to test for the presence of what? Nitrogen, the Gidal's test to test for nitrogen. So that information is there, how to test for halogens and all those things. Okay, they are all there. Then after knowing that carbon is there, hydrogen is there, then you do the quantitative analysis, and that will also tell you how much of each is there. Now, when you have this information, then it means that you can go ahead and calculate the empirical formula of the compound. The empirical formula of the compound. Please, is there anyone here who does not know how to determine or calculate for empirical formula? Because I'm not going to take you through that. This is something that we all know. If you are given, let's say carbon is 40%, hydrogen is 8%, oxygen is what? 56%. Usually the total composition should always sum up to 100 if it is in what percentage, okay? And then if maybe it is in mass or moles, when the mass is given to you, then the individual mass, when added up, should be the total of what? The mass of the sample. So when you have the composition of each one, carbon is 40, oxygen is 8, hydrogen is 8, oxygen is 56. Then the first thing is you divide each one of them by their atomic numbers. So carbon is 12, hydrogen is 1, oxygen is 16. So you divide 40 by 12, 8 by 1, 56 by 16. Then you get what we call the mole ratio. You get what you call the mole ratio between carbon, hydrogen, oxygen. Then you look out for the simplest mole ratio number and divide all through by the simplest mole ratio number. Okay. Then you get the mole ratio between carbon, hydrogen, oxygen, and that represents the empirical formula. So carbon, if carbon is 6, you write C6. If hydrogen is 8, H8. If oxygen is 2, O2. And that becomes the empirical formula. If after dividing by the simplest whole number ratio, there are decimals, the rule is that if the decimal is, let's say, 1.5 or 2.5, midway, then look out for a common factor that can multiply through and convert the decimal to the nearest whole number. If the decimals are close to whole numbers, please hold on and give me a minute. All right, thank you for don't worry, we'll be taking some few minutes break, but then so if the decimals are close to the nearest whole number, let's say you have something like 1.9. If it's 1.9, then there's no need of looking for a factor to multiply again. Just run the figure to the nearest whole number. So 1.9 is close to 2. So approximate to what? 2. If the decimal is, let's say, 1.1, 1.2, 1.3, those ones, run them down to the nearest whole number, which is what? 1. If it is 1.8, 1.9, 1.7, run it to the nearest whole number up. Okay. And then that gives you what? The empirical formula. Now, what is an empirical formula? Empirical formula expresses the simplest whole number ratio of the individual elements contained in a compound. So with this data of qualitative and quantitative analysis, that information is what we are able to use to calculate empirical and the molecular formula. So when you see any empirical formula and molecular formula question, the information that is given in there, they were obtained from what? Qualitative and then what? Quantitative analysis. Then, after knowing the empirical formula, okay, you then can measure or weigh the mass. When you know the mass of the compound, then you can go ahead and calculate the molecular formula. And there's a relationship. the empirical formula times N is equal to the molecular mass or molecular weight. So when you do that, you can then find the value of N. And when you find the value of N, this empirical formula times N is also equal to molecular formula. So when you get the value of N, then you multiply the N by the empirical formula, and that will give you what? The molecular formula. So in an empirical formula questions, we can give you the molecular weight, and you use it to find the molecular formula. If you are not giving molecular weight, but you are giving vapor pressure, okay, vapor pressure, there's a relationship between vapor pressure and molecular weight, okay? Whatever value that is given as vapor pressure, twice that is the molecular weight. So if the question does not give you molecular weight, but then they give you vapor pressure, multiply the vapor pressure by 2, and that will give you the molecular weight. And then you use it to find your molecular formula. So after finding your molecular formula, then, so when we talk about molecular formula, you see, I have defined empirical formula as what? The simplest whole number ratio of the individual element in a compound. Now, the molecular formula represents the actual whole number ratio of the individual element in the compound.
Yeah.
So if you take a compound like glucose,
Yeah.
its empirical formula is what? CH2O. But its molecular formula is what? C6H12O6.
Yeah.
Now, when you have done your molecular formula and you know the total number of carbon, hydrogen, oxygen, the total number of individual elements, then we can go ahead and determine other information which can help you to get to know the structural formula. So those ones, it is above this course, so I'll just mention the names. You can determine IR, that's infrared. You can determine the NMR, and the NMR, we have the proton NMR, we have the carbon-13 NMR. You can determine the X-ray crystallography. You can determine other information about the compound that can help you to also know the structure of the compound. So if you see any organic compound and you know the structure, if you know the structure of glucose, it wasn't by an accident. It wasn't that one person slept, woke up, and said that all of us, let us use this one as a structure. No. The process that I have taken you through this morning is the same process that all these compounds went through before we got to know their structures. They are experimentally determined. So the structure of glucose, the structure of thymol, the structure of what do you call it? Chloroquine, quinine, and the rest. This is how they all went through. In fact, the story that I was telling you about the cinchona tree, when they brought the extract and then they purify and then they determine everything, they realized that the compound that was in the cinchona tree, which was responsible for the cure of malaria, was found to be quinine. And I'm sure we all know quinine, or we've heard of quinine. One thing we only, I think we can easily identify with quinine is what? Its bitter taste. So for some years, quinine was or became the drug that was used to malaria in those years. Today, if you go to the hospital and you are sick, would they give you quinine? No, you will die, because with time, the malaria parasite developed resistance against the quinine. Then the chemist went back to the drawing board, look at the structure of quinine. Now, because we can synthesize organic compounds in the lab, which is contrary to the vital force theory, they came back, look at the structure of quinine, and they introduced chlorine to the structure, and then we had chloroquine. So when quinine was not able to do the work again, chloroquine became the next trade drug that was used to manage malaria for a long time. If you are sick and you go to the hospital, you are given chloroquine, either chloroquine tablet or chloroquine injection. Today, if you are sick of malaria and you go to a hospital, will they give you chloroquine? Chloroquine is even missing in action now, simply because chloroquine cannot even treat malaria again. The malaria parasite has developed resistance to it. But then the drug chloroquine, the chemists or the pharmaceutical industries will go back again, and then they keep on modifying, and then they come out with new anti-malaria drugs. So if you look at all the anti-malaria drugs, most of them, the Maladrin, the Malafan, the Artemether, is it Lufan or what? The Lonat. Yes, all of them. Yes, all of them. If you look at, you go and then buy them and you drink. That's all you do. But if you are to look at their structure, almost all of them have the quinine structure. Almost all of them. What it means is that it is the initial quinine that the pharmaceutical industries keep on modifying. Anytime a drug comes and then the parasite develop resistance, they go back and then change and modify some things. Then it becomes potent again. Then they will give it another name, or maybe the company will name it in a particular way. Do you understand? And then they keep on making money because we still have to get sick and then go and buy medicine and treat it. So all that I have just described now tells you that the over millions and billions of organic compounds are true. This is how we went about to even get to know their structures and then probably stay in the lab and produce them. Now, whenever you come out to the structure of an organic compound, the IR information, the infrared information, is able to help us to identify different functional groups. Different functional groups. And based on the different functional groups, we are able to classify organic compounds based on their functional groups. So as far as this particular course you have registered is concerned, Introduction to Organic Chemistry, we are only going to focus on only one of the functional group, which is called the hydrocarbons. So if you can see my lecture slide, there is a hydrocarbon slide captured there. But beyond the hydrocarbons, we have other functional groups like alcohols, ethers, epoxides, aldehydes, ketones, carboxylic acids, and then the derivatives, esters, amides, anhydrides, acyl chlorides, the amines, and a number of them. But this particular introduction to organic chemistry, we are going to focus on only the hydrocarbons. But then the one that you'll be doing in semester 2, we will continue from alcohols up to what? The amines. And then for the chemistry major, the battle will continue from there. You will be looking at other functional groups as we move on before you are done with your program. At this stage, I will open up if there are questions. If there are no questions, we would take a break, okay? Because it's our first meeting, please let me know if I'm moving too fast, okay? Let me know so I can slow down. The pace I'm moving is to ensure that we are able to cover all topics before the semester ends. And we have just 4 weekends meetings, and the workload is a lot. So there are some aspects I will plead with you. I might not even touch on it here. I will give you the lecture slides, and on your own, you should be able to be doing your personal learning as well. Any question? If there's no question,
sir, please. With the empirical formula,
yes.
If I heard you clear, you said you not touch on it. Anyway, is it part of this blog's content so that we also know what?
Yes, it is part. That's why it's part. That's why I've touched on it. And I'll show you how we calculate.
I have to calculate it. Some of us 70 years ago that we learned to.
Okay, so that is why if I give you the review questions and then the tutorial questions, now the difference here is that the tutorial questions comes without answers. So you have to solve them and then do group discussion with your colleagues, resort to the learning materials I'll be giving you, and then even colleagues who understand, let them help you. But then I also have the review questions. As for my review questions, it comes with answers. I'll give you maybe about 80 multiple choice questions, and their answers are all there. Now, the idea is not for you to go and learn the answers, please. The idea is when you read the question, you yourself solve it, check which one is the answer, then come and compare with the answer that has been provided and see whether you are right. Okay. If you go and learn only the answers.
And so please, are you going to get a slide for this course? That's chemistry. Are you going to get the entire slide for it today so that we can also photocopy it?
The one that we are doing today, the hydrocarbons, I've already shared on the page. I don't know whether you are all there. There are others I'll be sharing. At a point, I will be sharing some of them. I'll be giving to the center to share with you or your course reps. You are different centers. So your course reps can even reach out to me and I'll share with them. Then they can share with you because I'm sure the various centers have their own WhatsApp platforms, which when I share with the course reps, they can also give it to you there. Okay.
All right, sir.
So can we break now?
Yes, sir.
Okay, sir. Yes, sir.
So please, we are giving ourselves 15 minutes. 15. Now the 15 minutes, please, you can still leave your machine online, okay? And then go take some walk, go sip some water, go take some cocoa, okay? And then 15 minutes, that is 9:50, okay? Let's be back by 9:50. 9:50, let's all be back by 9:50. And then we'll continue. Thank you very much.
You're welcome, sir. You're welcome, sir.
Okay, thank you, sir.
Doc, I had wanted to add one thing before you go, but I don't know.
I'm here.
Concerning the slides, what you said you will be giving to the what do you call it?
Course rep.
Yeah, the course rep. Doc, I suggest that maybe you can drop it in the main page because some of us we don't belong to the same center. So if you can drop it on the main page so that we can have access to it, I think that one will be for everybody.
All right, that's what I've started doing. Yes, that the main page. It's not all of you who are doing introduction to organic chemistry. Some people are doing home econs.
Okay.
And then but then at this early stage, I'll be dropping them there. But with time, try and get your various centers, WhatsApp pages. Let me know the course reps. The course reps can. I think my contact has also been shared on the timetable with you, right?
Yes,
so you guys are free to reach out to me anytime. I'll always respond to calls. I respond to messages, and any challenge, I'm ready to attend to you.
But please, our first time meeting is on. So how do you even get to know our course reps since they are not in the various centers to know that these are our course reps?
Okay, please then listen. Now we have, because of your large numbers, we have some centers that I have appointed tutors, like Wesco. Do you have some Wesco people here? Wesco. Those people.
We heard that they have face to face.
and then online, Mauli and the other centers. Please, my lecture is fully online. So ours we will not be doing face to face. I am combining other centers who are not doing, who don't have teachers at their centers, and they are doing it all purely online. Okay, so mine is going to be purely online, and you will see me here throughout. But there are some centers I have appointed tutors who will be handling them face to face and online as well.
Hello, Doc.
The practicals, that one, it will not be online. You go to your center, okay? You go to your center. So when it is time for practicals, we will arrange and then give you all the information.
Okay, sir.
Let's take the break. When we come back, we can continue with the questions.
Thank you, sir.
Hello, police. Just said that he has shared the some of the slides on the page. Please, I cannot find it. Can you do that for me?
Yeah, I saw them this morning, but I wanted to open
Please,
some of the
which page? Which page is that?
now on the main page.
Again, I baby page is not baby. BS sign then switch baby.
It's very
Is it
difficult,
switch
but
3 biochemistry or switch 3.1 BS science? Yeah, join baby. Baby come back.
Switch 3.1. I want to. Okay.
Yeah, please, are you talking about the biochemistry group?
Let me count. Oh, I just open it right now. Introduction to organic chemistry.
But you be just a major no man. How this I enough and I mean,
Bruh, I was switch. Mine is switch 3.1 UCC. No.
Switch 3.1. And as
Switch
a group,
3.1.
you man.
UCC study center and as a say UCC then.
yeah, the problem here is the pages are many. So if you join many of them, you find difficult to get access to such information. But I think
Exactly.
No, but sometimes it's good you join many of the groups so that any notification you get access to whatever that you get it.
I suggest we share some contacts to ourselves so that if any information, we can just send it to our
So
colleagues.
this one they drop it in the
I think that would be the best. So I second what you just said. I think that would be the best. So I have to take your contact.
Okay.
At the different major group, and I've pinned it so you can go and
Sorry?
check. I said I've
Is
shared
anyone here at Tamale
Sir, you are
Center?
on which page?
Yeah, I said I've shared the documents into the chemistry major group, and I've pinned it so you can go and check.
So,
who's in Tamale?
Please, anyone?
So the chemistry major group you are talking about, you can add me there if I'm not there.
Yeah, I'm in Tamale Center.
Please, I guess we should create a group for Tamale Center.
Yes, we have to do that.
So
Please, I
right
would like
from
to
there,
know
we have
whether
to so that we can start
this
mobilizing things.
hello guys.
Yeah, the Kasakasa.
The last time I created for the Tamale Center, but like few people joined, so I will share the link to the one of the major groups,
Okay.
so that we
And
have.
then
Hello
share it
guys.
on the main web platform so
Okay,
that we
Okay, I
okay.
can
would like to ask whether this group is for charity major or is for all the community, those of us who are doing both major and minor. So,
That's
for
the
those
combined one, both
those
network
who are
and
doing,
mine. Because if you could recall
I
from
think
Doc,
I think this is the general case. Both major and minor, we are all doing it.
The group
I guess if
admin
you
for
recall
various
from
groups,
okay, fine, thank you.
the group admin for various groups, please add that to so that you can share the information to the groups respectively.
Nana, Nana,
Master,
say Nana.
master.
Yes, sir, please have you.
Can you give me your contact? I mean, yeah, you know me.
Okay, Pastor 0542
Zero
542
542
60
20.
606
Okay.
60 4741.
Uh-huh. What's 741?
Yes, please.
Yeah, please, which center are you?
I'm at Kaswa.
Okay.
Hello, guys. I think we can use the message to communicate because number
I know what you're talking about.
might be the number. But I think we can use
I don't know how you want to understand what you're talking about. I'm saying, what they your CS, you contact your CS and give him your list so that he will then insert your picture into this PV, and that's all. I know what you're talking about. We were previously used it, and then I don't know how you managed to move to that direction. Understand what you're talking about. I'm saying, what do you call it? Your CS.
Hello, good morning. Are we all back? I think the number is not encouraging. Please inform them to get back in so that we can continue. Please put a notice on your page that we are back.
Hello. Hello.
Hi.
Are we continuing the lectures, please?
Yes, let's
Yes, please,
continue.
but he has not started yet.
Okay, because it told us 9:50. That's what I'm asking.
Yes, he came. He came and he asked us to call all people back to the classroom. So we
Oh,
are
okay. All
yeah.
right.
But
Thank you very much.
You're welcome.
the number was not entirely when he was around, so that's why we said we should wait a little while.
Oh, okay. Okay. All right. Thank you very much.
But I think it's past 10, so let's start. Let's start. Those who are not here may later join. Let's start.
Yeah.
Hello.
Yeah.
Hello. Good
I think,
morning.
yeah, man.
All right. So please, this is our first meeting. So I am being a bit relaxed regarding the time. Okay. We gave ourselves 15 minutes and it's past that time, but a number of your colleagues were still not here. The challenge is that I wouldn't want to move and then they will come and it's like they wouldn't understand. That's why I'm being a bit relaxed. But in our subsequent meetings, we're really going to work within the time so that if you come late, then it will go against you. So I still have about 70 of you here, but we will have to continue. And then others can join in as and when. All right, so now on the screen is the hydrocarbons, which is one of the functional groups of organic compounds. So like I said, we have a number of functional groups. But then what is a functional group? Okay, a functional group is just an atom or a group of atoms, okay, that gives certain characteristic properties to an organic compound. It's a carbon or a group of, sorry, it's an atom or a group of atoms that gives specific characteristic property and behavior to an organic compound. So all those organic compounds which have that particular functional group, then we put them together. All those organic functional compounds that have a particular functional group, we put them together. So this functional group are used to classify them. That's why I said we have the hydrocarbons, we have the alcohols, we have the ethers, we have the epoxides, we have the aldehydes, ketones, carboxylic acids, amines, and the rest. But as far as this particular course is concerned, Introduction to Organic Chemistry, we are being asked to focus on only one of the functional groups, which is the hydrocarbon. So I'll be taking you through the hydrocarbons and then the classification there also. When we say a hydrocarbon, you should all be able to tell what they are. So I am defining it, and you can see on the screen that hydrocarbons are organic compounds that contains carbon and hydrogen only. So any organic compound that you see that contains carbon and hydrogen only is referred to as a hydrocarbon. A hydrocarbon. And one typical example of a hydrocarbon is methane gas, CH4, methane gas. We also have ethane and then other hydrocarbons. There are types of hydrocarbons. So you will see that under the hydrocarbons, they are classified into aliphatic and then aromatic. You have the aliphatic and then the aromatic. Now, the aliphatic ones are also further classified into the saturated aliphatic hydrocarbons and then the unsaturated aliphatic hydrocarbons. The saturated ones are what we call the alkanes. The unsaturated ones are what we call the alkenes and alkynes. So under aliphatic, you have the saturated, which are the alkanes, and then the unsaturated, which are the alkenes and alkynes. Then when it gets to the aromatic itself is also a whole course that the chemistry major people will be doing. But as far as this course is concerned, we are going to narrow ourselves to only the benzene chemistry. we will only talk about only the benzene. But then in your semester 3, that is those who be majoring in chemistry, we will pick only the aromatic and heterocyclic chemistry as a course, and then we'll go through into detail. So this is the classification of hydrocarbon. We have two main types, aliphatic hydrocarbons, aromatic hydrocarbons. The aliphatic is also further classified into the saturated, which are the alkanes, and then the unsaturated, which are the alkenes and then alkynes. So we are going to pick them one after the other. We pick the alkanes, we exhaust everything there. We'll pick alkenes, we exhaust everything there. We'll pick alkynes, we exhaust everything there. Then we end with what? The aromatic, and then that is the benzene. Then we are done for the course. For each class that we are going to pick, we'll be looking at their general formula, we'll be looking at their structure, we'll be looking at their nomenclature, how to name them, both their common name and then the IUPAC system of naming. We'll be looking at their physical properties, we'll be looking at isomerism, if there is, we'll be looking at their synthesis, how to prepare them, and then we'll be looking at their chemical properties or their reactions. So we'll look at all these things under alkanes. When you go to alkenes, we'll look at all this under alkenes. When you go to alkynes, the same thing. When you go to the benzene, the same thing. So now I begin with the alkanes, which are the saturated hydrocarbons. Now, they are saturated organic compounds and contain sigma bonds. They contain sigma bonds. I don't know whether you know the two types of bond, the sigma and then the pi bonds. The sigma bonds are formed as a result of what? Head-on overlap of atomic orbitals. So they are usually strong. Then the pi bonds are formed as a result of what? The lateral overlap between atomic orbitals, which makes them weak bonds. In fact, anytime we talk about the pi bonds, they are only found where we have multiple bonds, like a double bond or a triple bond. Whenever there's a double bond or a triple bond, that is where we find pi bonds. But for all single bonds, they are sigma type of bond. So alkanes do not have pi bonds. Take note, alkanes do not have pi bonds. They only have what? Sigma bond, which is a single bond. The general formula for alkanes, as you can see on the screen, is C2H2N plus 2. C2H2N plus 2. Okay, that is the general formula for alkanes. CnH2n plus 2, where n is an integer from 1, 2, 3, 4, 5 up to infinity. The value of n is an integer from 1, 2, 3 up to infinity. So if n is 1, then when you put that 1 into this formula, then you get what? CH4. Ideally, it should have been C1H4. But when there is 1, the number 1 as a subscript to an atom, we don't write the 1. It is from 2, 3, 4 going that we write it. So the C here means that it is C1, but we don't write the 1. So if n is 1, then it's going to be C1, 2 times 1 is 2, plus 2, 4. So you get C1H4, which is the same as what? CH4. If n is 2, then it will be C2. When we come to the hydrogen, 2 times 2 is 4, plus 2, which is 6. So C2H6. If n is 3, C3H8. If n is 4, C4H10. So when you know the formula of alkanes, then you can derive all the members of the alkane family. I want somebody to tell me, what will be the alkane formula if N is 6? If N is 6. Yes, anyone?
Yeah, it will be
Hello, sir.
Hello.
Go ahead.
H14.
Yes,
C6H14.
Yes, C6H14. You are right. Another one. If N is 8.
CH18.
What about if N is 10?
C10
H22.
Say, I have questions.
Well, I'll let you ask your question. Hold on for me now. What about if N is 1,000?
C1000 H2002.
Yes.
So
3,000 H2002.
and 2002. Exactly.
Great. So what it means is that with the formula of alkanes, no matter the number of carbons, we can derive all the members. Okay. Now let me hold on and then take that question before I continue. Somebody wanted to ask a question.
Say, please, according to the introduction, you said that the alkanes are the C bond, that's carbon. But like when you are asking the question, you said that if N is 6, if N is this, so I didn't understand that part. Why not asking what if H is this?
Your question is not clear to me. I don't know if you can come again.
Like when you are asking of the formula how to derive all the alkanes, you are
Yes.
asking if N is 6, if N is 6, but you are not rather asking if H is this one. So that is the place I got missing.
If H. No, you see, we have already defined hydrocarbons. They contain carbon and hydrogen only. Okay.
Yes.
And the formula there is what? Cn.
Yes.
H2n plus 2. So now the
Yes.
variable here is n. What is n? And I've defined n as n is an integer, which can be 1, it can be 2, it can be 3,
Okay.
it can be 4, it can be 5, up to infinite. So when I give you the value of n, you should be able to tell me the formula.
So that means the formula can be CnHn. So
But then we are looking at alkane, and the formula there is what? CnH2n plus 2.
Okay.
And I've
I
defined
understand
n.
now.
Good. Good.
I understand.
Great. So we're still on it. Now, looking at when n is 1, the formula there, n is 2, the formula there, n is 3, the formula there. There's something that is so peculiar and runs through. And that is, you can see that from the first member to the second member, look at the number of carbons. There's a difference of what? 1 carbon, isn't it?
Yes.
And there's a difference of 2 hydrogens. And there's a difference of 2 hydrogens.
Yes.
Oh, yeah. Exactly, sir.
Good. So that is what we call a methylene group. A methylene group. Okay. That's what we call a methylene group, CH2. Now, that methylene group runs through such that from one member to another, there is a difference of what? A CH2 group. There is a difference of what? CH2 group. Meaning, if you are from the first member to the second, there's a difference of CH2. okay? And then if you are from the second to the third member, again, there's a difference of what? A CH2. And from the third to the fourth, the same thing. So this particular phenomenon, this particular unique characteristics that we are seeing in our alkanes is what we call homologous series. Homologous series. So we say alkanes exhibit homologous series. Alkanes, they exhibit homologous series because moving from one member to the other, there is a difference of what? A CH2 group. There is a difference of what? A CH2 group. That is a methylene group. So we say they show homologous series. Homologous series. From this to this, there's a CH2. From this to this, there's a CH2. From this to this, CH2. So alkanes exhibit homologous series. And that is what it implies. Now let's look at the structure and shape of alkanes. We've already said that alkanes are saturated and that all the bond type in alkanes are single bonds. So if you are drawing the structure of an alkane, you are not supposed to see a double bond. You are not supposed to see a triple bond. All you see across should be single bonds. So if you take the first member, which is CH4, this is the structure of that, as you can see here. Now, the carbon atom, I think I need to also say something, but maybe it's not too late. You see, we're saying that organic compounds are compounds of carbon and that there are millions of these compounds. The question is, what is so unique about carbon that carbon is able to have so many compounds? And one of them is that carbon has an ability to form carbon-carbon single bond, carbon-carbon double bond, carbon-carbon triple bond with itself. The same carbon is able to form carbon single bond, carbon double bond, carbon triple bond with other elements. Now, the same carbon is able to form what? Compounds of rings. All the compounds of carbon are not straight chain. We have cyclo or ring compounds. Again, the carbon is able to form long chain hydrocarbons. You know, carbon can bond to itself for 100 carbons, and that is only attributed to carbon. Other elements cannot join to themselves, you know, in that kind of chain. The carbon is able to do that. So this characteristics, okay, makes carbon unique. And that is why it is able to form millions of organic compounds. So over here, carbon is tetravalent. When we say carbon is tetravalent, what it means that carbon can form 4 bonds maximum. At any given time, carbon should form what? 4 bonds. That's why we say it's what tetravalent. So if you remember your hybridization concept, I don't know whether you still remember hybridization. If you write the Bohr's model of the configuration of carbon, you get 1s2, 2s1, 2px1, 2py1, 2pz1. So what it means is that the atomic orbitals that has to be mixed to form bonds in terms of carbon, we have what? 1s orbital mixing with what? 3p orbitals. So the type of hybridization in carbon is what? sp3 hybridization. Now the 4 orbitals that you are missing for carbon atom to form bonds results in what? 4 hybrid orbitals. And that results in why carbon can form 4 bonds. This is hybridization. I don't know whether you still remember that. So carbon is tetravalent, can form 4 bonds. Hydrogen is monovalent and can form 1 bond. So as you can see in the structure, the carbon atom here is bonded to what? Hydrogens 4 times, and that is the maximum. Whilst each hydrogen can form only one bond because it's monovalent. And that explains the planar shape of what? Alkane. Okay, so alkanes have a planar shape, and this is that of methane. But if you look at the three-dimensional shape, of carbon, alkanes, it is tetrahedral in structure. The three-dimensional shape of alkanes is what? Tetrahedral. So as you can see on the screen, the yellow, background diagram, again, carbon is bonded to 4 different atoms. But in the three-dimensional structure, you see that one of the hydrogen is on the broken line. In chemistry, when you see any group bonded and then we are using broken line, it means that though that hydrogen is there and is bonded to carbon, that hydrogen is hidden. You can't see it. Over here on the screen, you can see all the 4 hydrogens. But in reality, there's no way you can see all the 4 hydrogens on carbon. One of them will always be hiding behind the carbon. And that one is what we use broken line to represent. And this represents the tetrahedral structure in alkanes. So that is the structure of alkanes. Now let's go to nomenclature. How do we name them? Of course, if you give birth to a baby, one of the initial things you go to do is to prepare and then you name the baby, isn't it? I'm not sure you give birth to your own child and then you say that somebody should come and name the person for you. And the name you give to your baby is a characteristic or a true reflection of your family. So you see, sometimes you add your family name to it. And then sometimes to religious, you might add your religious name, what we call the Christian name or the Muslim name, to also give you an indication of the identity that this person is a Christian or this person is a Muslim. Okay. And then the family name, at least to let people know that, oh, this person is from this family, he comes from this family, or he comes from this area or this region. The same way, every organic compound must be given a name just to identify them. Every organic compound. So for our case, we are going to name them. But then, in the naming system, we have what we call the common names, and then we have what we call the systematic names. The common names usually are not accepted everywhere because sometimes it might not be understood by other people when you cross border your country. If this class, which I have about 90 people here, if we have about 3 or more guys who were born on Wednesday, and so they have the name Kwaku. If I mention the name Kwaku right now, all of them are likely to respond. And so that makes Kwaku what? A common name. In the case of the English name, maybe we might have Emmanuel, about 8 people called Emmanuel here. If I just mention Emmanuel, you realize that all the Emmanuel people here might respond. So here, Emmanuel becomes a common name. But I can mention one particular name and only one person will respond. Bashiru Adamu Ayong. Bashiru Adamu Ayong. And one person will respond. Why? Because the name given encompasses the surname, the Muslim name, and then maybe the family name. And he's the only person who has that particular identity. And so in that case, that is not a common name, but that is a systematic name. Because Wherever you go, he's the only one with that name. So in the case of organic compounds too, we have common names, and the common names, some of them, everywhere you go, the same, that's how they all call it. But some places, if you go with certain common names, they wouldn't know that, oh, this is the compound you are referring to. A common name like benzene, whenever you are learning benzene, whether it is Ghana, whether it is Europe, whether it is America, whether it is Asia, when you say benzene, everybody knows benzene. Benzene is a common name though, but it's accepted everywhere. So for the nomenclature of alkanes, we will be looking at some common names as well as what? The IUPAC names. And we should all be able to name any alkane that will be given to us in an exams. Now, the table you see on the screen contains alkanes from carbon 1, 2, 3 up to 100. But then our focus is on the first 20. The first 20, everybody here should know. All of you should know. The first 20. So from the first, that's carbon 1, we have methane, carbon 2, ethane, propane, butane, pentane, hexane, heptane, octane, nonane, decane, undecane, dodecane, tridecane, tetradecane, pentadecane, hexadecane, heptadecane, octadecane, nonadecane, and the 20 is what? Icosane. Please, all of you should know these first 20 arcane names because it's going to help you a lot. You should have them at the tip of your fingers. When I call your name and I ask you from carbon 1 to 20, give me the names of all the arcanes. You should be able to do that. Is there anyone here who cannot do that? Is there anyone here?
Yes, we are now going to memorize them.
You don't have to memorize it. It's something that when you look at it like this, mistake. Or you are old like myself. If you are old like myself, then you will
Very,
struggle.
very old. Very old.
If you are old like myself, if you are old like myself, where you have even family responsibilities, payment of school fees, and other things, then you're going to struggle.
Plenty of us are here.
Oh, I
We are
see. You are
many.
not alone.
So I think if there could be a trick, if there could be a shortcut, now to get them straight up.
Shortcuts are always dangerous. Shortcuts are always dangerous, you know. But then you could see, okay, from methane, ethane, propane, butane. Is that right? The first four, which are usually gases. From pentane, you see, we are making use of this. Is it how do you call it? Is it Roman
polygons?
Yeah.
Yeah,
Pent is
polygons.
5.
Polygons.
Okay, pent is 5. Hex is 6.
Yeah.
Step is 7. Oct is 8. Do you understand? And then you get to 10. Then, if you also check from the 13 coming, okay, tri means 3, tetra means 4, penta means 5. So tridecane 13, tetradecane 14, pentadecane 15, hexa means 6, hepta 7, octa 8. So yes, in fact, there is some trick in there that you can use to get all of them easily. Yeah, the 20 is icosane. So please, this is your assignment number 1. Make
Sir,
sure.
please, you said 20. How do you pronounce it? I'm seeing EX.
Yes.
Is it not EX?
Please, the spelling is EICOSANE. Icosane.
Wow.
All right. So know this. And then these are the unbranched alkanes. They are all straight chain. They are not branched. And when you know this, they form a parent name even when we get to the branch examples. Okay. So note them. Now, the IUPAC names comes with a set of rules. Okay. It comes with a set of rules, but you can see that the alkanes, they all end with what? ANE. Okay, their names. They all end with what? So methane, ethane, propane, butane, pentane, and so on and so forth. Now, because the world of chemistry is orderly presented, we didn't want a situation whereby I will sit in Cape Coast here and then give any name I want to an organic compound. You would also sit where you are and give any name to an organic compound. So there is this group we refer to as what? IUPAC. And IUPAC is what? International Union of Pure and Applied Chemistry. This body came out with what? A selected rule, okay, which is like your 10 commandments, which is like your this thing, your Bible or your Quran, okay, the commandment in it, which you have to follow rigorously in naming organic compounds. If you are conversant with these rules, if you are very, 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 in tune with these rules, then any organic compound that will be given to you, you follow the rules and you should be able to name it. You should be able to name it. So I'll be taking you through the rules and the alkanes. When we get to alkanes, there'll be a little modification. When we get to alkynes, there'll be a little modification and so on and so forth. So if you are naming an alkane, an example is what you can see here. Please, are you also conversant with this dot line method of writing the structures? You see, sometimes we use the CH3, CH2, CH2, and then sometimes we use this dot line method. Let me find out whether you are conversant with this one, because most of the structures I will be drawing for you, I'm going to use the dots, this one, the dot line structures. This one.
Please, I'm not conversant with this.
Same here, sir. We are not commenting on them. Maybe
Who-
you can elaborate.
Same here. We are not
But then the truth is that we have not even started organic chemistry proper. All these ones are just introduction. Anyway, all right. I'll do my best. I'll do my best and then get you along. Okay, so please.
The lesson.
Is there a question? Can you see my arrow?
Yes, please.
Can you see my arrow?
Yes, sir.
All right.
Yes, please. I see.
Good. Now,
Yes, sir. Yes, sir.
beginning of any line is a carbon. And where that particular line ends is also a carbon. So this is a line. So it starts with a carbon and it ends at a carbon. Then the second one to this line here, there's a carbon here. Then there's a carbon here. There's a carbon here. There's a carbon here. Then down here too, there's a carbon here. Please, is that one okay at this point?
Memory now shows carbon.
Yes, sir.
Yes, sir.
Good. So can somebody tell me how many carbons are here? Based on the information I've given. I have to let you understand this one.
Seven carbon.
Hello, boss.
Yes, seven carbons. Good.
Yes.
Very good. Now, this is an alkane, and there are 7 carbons. So it tells you that even you can get to know the formula of this carbon. So that will be C7H16. C7H16. Okay.
Oh, so simple.
You see the formula. Now, beginning of a line which we are saying there's a carbon, that carbon is bonded to this carbon here. And I've already told you that a carbon should have how many bonds? 4, isn't it?
Yeah,
So
4. Maximum 4.
It means that this first carbon here, where the number 6 is, that one has 3 hydrogens on it. But we don't write the hydrogen in the dot line structure. We don't bring the hydrogens. So as you see the carbon here, it means it has 3 hydrogens on it. Is that clear?
Yes. Yes.
So this carbon here will have 3 hydrogens. This one will have 3 hydrogens. Those at the beginning, at the end of the chain, they always have 3 hydrogens. Now let's look at the carbon labeled 5. You see that carbon here is bonded to the carbon number 6. And it's also bonded to carbon number 4, isn't it?
Yes.
So it means out of the 4 bonds, we'll be able to identify 2. So there are 2 more left. Now that 2 left is going to be bonded to hydrogen. So it means that the carbon 5 here has 2 hydrogens on it. But we don't write. The carbon 4 here will have 2 hydrogens on it. Carbon 3 here will have 2 hydrogens on it. Now, when we come to the carbon 2, that carbon here, you see that it is bonded to the carbon here, 1. Yes. It's bonded to the carbon here, 2. And it's bonded to the carbon here, 3. So it has how many bonds? 3. So how many left? 1.
1.
So that one,
one hydrogen.
represents a hydrogen bond. So there's only 1 hydrogen on this carbon labeled 2.
Very
You see, it's not that difficult. You see, you are getting it.
Yeah.
So, one more.
So please,
Yes.
if you can take us through once again.
You know, I will not do that. And why? You know, I will not do that.
Doug,
And
please
why,
continue.
why I will not do that is that if I'm to do that, we might not go anywhere. We might not finish our target. And me, whether we finish or we don't finish, my questions will cover every aspect. So let me move on. I am trying to see. Please, I'm just trying to see whether you can see something. I've on my video. Can you see my video? Can you see my video, please?
Sir, please.
No, sir.
Yes, we can.
Is that
please?
very good? Okay, hold on. I think I've disabled it, but I am going to do something. The one that you can see, the dot line structure that you can see, and per the information I've given you, I have rewritten that structure using the normal structure, that is the CH3 bonding CH2. So I am shortening it and I'm putting it on the main page. Okay, your WhatsApp page. Please go there and see how it has been rewritten in the normal way of using the atoms.
Noted.
I am sharing it. Let me see. Cohort switch, cohort 3. Ready? All right. Please, I've shared it there. So go and check. It's not that clear, but I think you can see how I have added all the carbons and hydrogens to it for you to see and compare with what is here. Kindly go there, check, and then we get back. All right, please. It's okay.
Please, number two. Number two. How many hydrogen atoms will be bonded to number two?
Those who are responding, it's okay. Don't go and respond plenty. You'll be disturbing other people. Don't go and respond everything there. Those who are saying okay, it's okay. Don't go. All of you should not go and write there. Yes. Is it Max? Max has also done his own and shared there, and that is good. He had even expanded the hydrogens for us to see the carbons bonding hydrogens. Yeah, it's the same thing. Max, it's the same thing. All right. So when you see things like this, don't think that it is a KG1 drawing, or it is some visual art. It's an organic compound that you can see there. It is not maybe your child or your daughter or your son's KG drawing that he or she has brought home. This one is organic compound.
Let's continue.
All right. So when we are looking at the IUPAC rules, the first one is select the longest continuous carbon chain. Select the longest continuous carbon chain. Now a chain starts from one point and ends at another. So for the same structure on the screen, my chain can be 1, 2, 3, 4, 5, 6. I can also start from here. 1, 2, 3. I can also start from here. 1, 2, 3, 4, 5, 6. So there are 3 possible routes. Okay. 2 of them are 6, and then the third one is 3. So the question is, which one is the longest? It is the 6. Is that right?
Yeah.
Yeah.
Now, a 6 longest carbon chain. That's why I asked you to learn the first 20. The first 20 straight chain. A 6 carbon straight chain is called what? Hexane. It's called hexane. So if you don't know this first 20, then it will affect you or to worry you in your nomenclature, how to name alkanes. That is why I gave it as an assignment that all of you try and be very conversant with carbon 1, methane, all the way to hydrogen. So the longest chain is 6. So that one is what? Hexane.
Oh, don't worry.
Hey, let me meet this gentleman. All right. As for some of you, you are always laughing when people are anyway. So now we know the longest chain to be 6, which is hexane. But you realize that after selecting your longest chain, which is 6, and you are calling it what? Hexane, there is still another carbon which is down here. It is branch. Okay, that one is branch. That one cannot be ignored. It should also be part of your name. So apart from the carbon atoms in the longest chain, those that do not form part of the longest chain, they are called substituents. They are called what? Substituents or substituent groups. Now, substituents are also to be part of the name. Now, the substituent group here, how many carbons do you have there? How many carbons do you have in the substituent?
1.
It's 1. Good. Now, how do you call a one carbon alkane?
Methane.
Methane. Good. But because the parent name has been identified as hexane, the substituent, you cannot also just say methane. When we say it's a substituent, it means it has lost one hydrogen. So when methane loses one hydrogen, it becomes methyl. It becomes what?
Methyl.
That is M E T H Y L. M E T H Y L. I'm just trying to write it so that those people can see. Okay, please, can you see the meter written there?
Yes, sir.
So because it's a substituent, in naming the substituent, the last three letters, A-N-E, the A-N-E, you replace it with what? Y-L. You replace what? Y-L. So methane becomes methyl. Ethane will become what? Ethyl. What will propane be? Can somebody tell me propane?
Propan.
Good. What about butane?
Butan.
Butyl. What about
Butyl.
pentane? Pentyl. Good. So that is the substituent name. Okay. Now, IUPAC is saying that the substituent name must precede the parent name. The parent name is the longest chain, which is 6 carbon, hexane. Now, the substituent name, methyl, should precede the parent name. So, this particular compound you see on the screen is going to be what? Methyl hexane. Methyl what? Hexane. Then the next IUPAC rule says that now the subsequent group, okay, on the longest chain, it is not found on any of the carbons. It is in a particular location. So number the longest chain. Number the longest chain such that it will give the least number to the subsequent group. So if I'm to number from right to left, as it has been done, what is the position of the methyl group? It's not number what? 2. But if I were to have numbered from left to right, if I were to have moved from left to right, it would be 1, 2, 3, 4, 5. Okay. So now 2 and 5, which one is the least number?
2.
So IPAC is saying that we should, times like this, and then people are giving us feedback. It is very, very, very difficult because if you don't get it, you are out. Okay, so this aspect, I'm taking my time. If you don't get the concept, the rules, and apply, any compound I'll give you to name, you cannot name it. So please, those who are giving us feedback, let's pay attention, please. Now, IPAC is saying that if you number the longest chain, number it in such a way that you give the least number to the substituent. Now, when we check the 2 numbering, we have 2 and then 5. And we are saying that 2 is the least. So we prefer to number from right to left so that the substituent position will be 2 instead of 5. Now, that number 2 is the position of the substituent, and that one must precede the name. So before the meter, you bring 2 in front. Okay, so you bring 2, and then after writing the 2, you bring hyphen. Okay, you bring hyphen like this. So you have what? 2 meter. Now the 2 in front of the meter is telling you the position of the substituent group meter. So the name will be 2 meter hexane. 2 meter hexane. And that will be the IUPAC name for this compound. 2 meter hexane. Now let's look at other examples. If 2 different chains of equal length are present, choose the one with the larger number of branch points. So look at this one, as you can see here. The longest chain is 1, 2, 3, 4, 5, 6. Okay, 1, 2, 3, 4, 5, 6. Then we have 1, 2, 3. 1, 2, 3, 4, 5. So you have a chain of 3, a chain of 5, a chain of 6. So the longest one is what? 6.
6.
When you come to this one, okay, the first one, you could see that if you consider the 6, then it means that the one that I've circled with red, they are what? Substituent groups. They are not part of the longest chain, so they are considered as what? Substituent. So how many substituents do we have here? We have 2. A 1 carbon substituent, which is methyl, and a 2 carbon substituent, which is what? Ethyl. Now, if you don't do it that way, and then you also count the longest chain from here, 1, 2, 3, 4, 5, 6. This 2 is another long chain of 6. But this long chain of 6, it means that the group that is substituent is this one, the one that I've circled with red. Between the 2, we prefer the first one because the first one has 2 different substituents, but then the second one has only 1. IUPAC is saying that though the 2 of them have the longest chain to be 6, here it is 6, here it's also 6, they think that the best form is to select the one that has what? More branching or more side chain. And that becomes your longest chain and then appropriate for your naming. Then you number so that you give the least number to the substituent. If you number as it has been done here, then the methyl group here is what? 2. And then the ethyl group here is what? 3. Assuming you were to have numbered from here, if you were to have numbered from here where the 6 is, the ethyl would have been what? 4. And then the methyl would have been what? 5. Okay. So 2, 3, and then 4, 5. Which one is giving you the least number?
2.
2 and 3. Yes.
The 2.
The 2 and 3 is giving you the least numbering as compared to the 4 and 5. So we'll choose the one that is giving us the least numbering. Now, after that, you can see that unlike the first example I gave you, this one, the substituents are 2. So the question then is, which one should you bring first? Because the substituent should be named before the parent name. The parent is 6, so it's going to be what? Hexane. But then the methyl and then the ethyl. We know that the methyl is what? 2, so it's going to be what? 2 methyl, and then the ethyl is position 3, so it's going to be what? 3 ethyl. But we are saying that in arranging them, which one comes first? That is the question.
The letter, the ABC, the one which comes first, E.
Yes. So
the ethyl comes first.
So the IUPAC is saying that when you have 2 substituents, okay, like methyl and ethyl, arrange them in alphabetical order. Methyl starts with M, letter M. Ethyl starts with what? Letter E. So E and M, which one comes first? It's E. So when you are writing, also arrange them in what? Alphabetical order. So it means that the name will be what? 3 eta 2 meter. I'll bring this one in your exams. This same one, this same structure, I'll bring it in your exams. Okay. So when you get it wrong,
But I hope you will send the slides with us.
I've already done that. It's with you. It's already with you. The slides are already with you. So please check.
We'll do that. Okay, I'm not.
All right.
I was not.
All right. So let's move on. Still on the naming of our kings. Oh, our time is up. Now, you see another one here, and you could see that the longest chain is 1, 2, 3, 4, 5, 6, 7, 8, 9. This one, 1, 2, 3, 4, 5, 6. This one, 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7, 8. So you have to look at all the possible chains. So we have 4, we have 5, we have 8, we have 9. 1, 2, 3, 4, 5. Then the question is which one is the longest, and it is the 9. So the 9 becomes your parent name, which is no name. Any other group that is not part of the longest chain is considered as what? A substituent. And here, if you look at the substituent, we have what? This one, which is meter. We have this one, which is what? Meter. Then we have this one, which is what? Ether. Now, you see, life is short, okay? So we don't have to waste time. So IUPAC is saying that instead of the 2 meter groups here, you see, we have numbered it so that we have 3 meter, 4 meter, and then 7 meter, okay? That is giving us 3, 4, 7, the numbers. If you are to start from where the 9 is, then you are going to get what? 3, 6, 7. And 3, 6, 7 and 3, 4, 7. The 3, 4, 7 is the least, isn't it? So
yes, it is.
Saying that, please, where you have 2 of the same substituent, like meter, you don't have to write them separate and say 4 meter, 7 meter. Life is short, so we don't have time for you to be writing them separate. In such a situation, you have to use the preface die if they are 2, tri if they are 3, tetra if they are 4. Okay, so you bring their positions 4, 7 diameter. 4, 7 diameter, as you can see here. Between the 4 and 7 is a comma to separate the positions. It means that one of the meter is on position 4, the other one is on position 7. Now the die here means that there are 2 of the meter groups, and they are on position 4 and 7. But then again, meter and ether, you have to arrange them alphabetically, and E comes before M. Please don't use the die as the alphabetical this thing to arrange. The die is just a preface to show that there are 2 meter groups, but the actual substituent name is what? Meter, and it starts with M. So don't go and say that, oh, but D comes before E. No. The die here is just a preface that there are 2 of the meter groups. So it's going to be 3 eta, 4, 7 diameter, no name. Please take note of this. Between a position and a name, there should always be a hyphen. After a name to another position, there should be a hyphen. Between 2 positions, there should be a comma. As you can see, take note of this. It's very, very important. Please, do you have another class right now? When is your next class?
Yes.
11.
So you might need some time to go and prepare for it, right?
I think the class has been postponed to tomorrow. It has been scheduled for tomorrow.
No, that's your class.
Anyway,
Okay.
anyway, I
That is
also have another class. So after speaking for 5 hours, I also need to rest before my next 4 hours class, which is at 11:50. But then the screen, you can see a number of structures. These ones are not the dot line structure. Okay, these are the normal structures. So check the structure and check the name and see whether it makes sense. This is your assignment. The names are there, but just go and look at it, the way we have numbered it and the way the name has been derived here. One thing I want to add is that when you have apart from the ether, meter, proper that we talk about, when you have the inorganic substituents like bromine, if you see a bromine, okay, if it's a substituent, it's called bromo. If you see chlorine, it is what? Chloro. If you see iodine, it's what? Iodo. If you see those halogens, fluorine is what? Fluorine. So please, when you see them that way, know how to write them. Then again, when there is an organic substituent and then inorganic substituent, okay, like this one, you see there are two inorganic substituents, bromo and iodo. So you have to arrange them in alphabetical order. Bromo comes before iodo. B comes before I. Again, the inorganic should always come before the organic substituent. The organic substituents are those that has carbon in them. So methyl is organic substituent. Iodo is inorganic. Bromo is inorganic. Always name inorganic first before organic. And when you have two or more of the inorganic, arrange them in alphabetical order. When you have two or more of the organic, also arrange them in alphabetical order. But each substituent should have its position indicated before it in the name. So go and look at this one and then make sure you appreciate and understand the names. These are semi-systematic or common names, which we need to know. But then I would want to end the class so that you prepare for your next class, and then I also prepare for my next class. Please, the workload is a lot, and so we need to do a lot of the work ourselves. I have shared this slide, okay, with you on your page. Get it, and please, from now till we meet next week, go through the rest yourself, so that when we meet next week, I wouldn't have to waste more time, okay, to finish the arcanes so that we can move straight to the arcanes. I hope that is fine.
Yes, sir. Yes, sir.
Yes, sir. Yes, sir.
Yes, sir.
I don't know whether those of you who will major in chemistry, whether the chemistry major, whether you have a WhatsApp platform. Please kindly add me there. Because for the chemistry major alone, I know you might not be many, so I can manage with most of the discussions over there with you. You can add me there. Okay.
Okay, sir.
All right. Any question? Any contribution? All right. So we end for.
Please, we don't having chemistry as minor. Are we also going to do the same thing with those in as major?
When you say the same thing, what do you mean by the same thing?
What we have started with, is it going to be the same for those having it as major?
No, he has clarified.
But you are already, all of you are doing this course, introduction. Okay.
Yes, what did I
All of
say?
them
Yes,
register this one. And then you have registered.
Introduction body.
Please, you ask a question. Listen. If you don't want to
you know.
let me
Now, I'm far away now. Okay.
So you have all registered for this course and then the practical. So you're all doing it together.
Okay.
This is block 1. In the block 2, there will be some chemistry courses. You are going to do it together. Then when you get to the semester 2, I will come and continue this introduction course. That one will be general organic chemistry. That one, whether biology major, physics major, or chemistry major, all of you are doing it. And then it's practical. It is the block 2 of the semester 2 that you see that the chemistry people will be doing some extra chemistry courses. You, the biology, you will not be doing. The same way you also will be doing some biology courses, the chemistry major will not be doing. Those are electives. So something like main group, only the chemistry major will do it. Natural product, only the chemistry major will do it. Stereochemistry, only the major people will do it. So it's not everything that you do register the same. In fact, when they mount it, you will see the difference. Thank you.
Thank you very much.
All right. Bye for now. Have a nice day.
Thank you. God bless you.
Bye.
Chale abuafo mumwe nene adie kuku edie.
Enyo kura.
The person at the church where they only pay muso crowd.
Okay.
Hello. Chemistry, major chemistry for me.
Biology, what the chemistry.
Hello.
So when are we having our next lesson?
I think 11:30 to 4 is a bit of biology.
11:30.
Maybe somebody at all practice.
Okay, they are
Hello.
Ariane da su rinje kire mu. Emma na nwo na mo ko so mu nje kire mu.
Emma ne.
Emma na mo ko nje kire mu.
Sasa no era mi tia so na kana
Monterrey na ye na TV bi.
Die na.
Sorry,
Emma na bi shako.
Ade enda fomo, Charlie. Ade ye hunu sana.
Emma na bi shako so mu mo.
Hello.
You say your piece, madam.
Hello.
Madam, you say your piece. You are shako.
Hello, madam.
Yes, boy.
But
Madam Patient.
Yeah. Hello.
Oh, you tell boy kasa.
I am more subscribed to Nest Blight. Why? Nest Blight. Why? Obetire mu yi ono no videos ni ade obetire mu yi ma wa hu yi passing we. Ya mo na
Ne link we on ban to we ne link we ni ehu. Masa obedi ahin kura na obeti me beti ase de beti o.
Oh, but just say,
Ahin.
I'm saying, I bet you don't watch that, Papa.
Nti ne
Kasa,
link
Papa.
we. Nti yo pente mo ne link we.
My baby, why them? In fact, speeding good on your local.
Yeah, easy.
Wo ye be ya private teacher bi
I
a
didn't
do a
study
private class bi su kura kan ho a. Nka so be boy masa.
because I didn't
Hello.
know to me about 3 or 4 examples now. What you mean? First one
But
here,
you,
I say,
Uti,
I say,
your
that's
friend,
not the in an American.
Oko YouTube, I know about Nest Blight, why I know. Or
NS
Nigerian, or
Bright.
Chile,
Okay.
NS
and
Bright.
Jonah Emmanuel, why?
NS
We are
Bright.
the pa, we are the papa, we are there. One case when you
But
bet
some of
when
the
you bet
DNA, and as done
Nest Blight.
That be
NS
specify only
NS.
Okay. NURSE, Nest.
next,
Yes.
then right. You
Uh-huh.
know,
NS.
Jonah Day. You know,
But
Jonah
so,
Day. You know, Jonah Day.
Jonah Emmanuel, why?
Emmanuel.
Omo yard papa
YouTube.
wan kasa obi hu omo yard ya wan kasa wani beji chemistry no omo yard papa
Okay.
now bright on
That's
spelling
it.
is it.
bajo B R
Yes.
I G H T
Okay, next if we are
ai ono ye nesi ni agaza
okay.
aha
Next bright. Okay.
we ni na wa chere da njo obet o chere ni ye papa endu akwa na o chere
The next class, biology major for an answer. Both chemistry and biology. For example, so next class, chemistry, both chemistry major for me, biology for an answer, biology major for one.
You came across this question in your chemistry exam. How will you solve it? It's actually very easy. From the look of things, this particular question is on IUPAC nomenclature, okay, meaning how to name organic compounds. And with this question, I'll be explaining the overview on how this aspect of chemistry works. So please watch closely. So the first thing we have to do when we have to name an organic compound is to identify the longest continuous carbon chain. You look at the compound and try to look at the part of the compound that carbons were connected together, and you try to determine the one that was longest. So in the look of things, this is horizontal should be the longest continuous carbon chain. So this can also be a long continuous carbon chain as well. But since we had it to be, now the reason why I said that is because if you look at it horizontally, you see that we have 4 carbons connected together. This carbon, this carbon, this carbon, this carbon, and they are 4. If you still look at it in this direction, you see that this is also another long continuous carbon chain, and it's still 4 carbons connected together. So my point here is this: what you have to note here, you have to make sure that you identify the longest continuous carbon chain. Look at the compound carefully to know the carbon-carbon connection that was longest. And in the look of things, both directions to which I will count can actually be the longest. So let's just take the horizontal fashion. So we've identified the longest continuous carbon chain to be in this fashion. So the next thing, we have to number the longest continuous carbon chain. Please, I said number. So you number in both directions. You number forward and also you number backward. Meaning that I will start by saying number 1, number 2, number 3, and number 4. I will number backward as well. 1, 2, 3, and 4. So after you've done that, since we've actually numbered, we've seen that at the end of numbering, how many carbons did we get? we got 4 carbons, meaning that this compound should be called a bute. Remember, a 4-carbon compound should be called bute. 4-carbon organic compound, they call it bute. Do you understand? So if it's a single bonded compound, it should be called butane, because single bonded compounds, they are called alkanes, double bonded compounds are called alkenes, and triple bonded compounds are called alkynes. So in the look of things, we tried to identify the longest continuous carbon chain and numbered it and also named it. So we saw that we had buttes. Now, moving further, it's actually very easy. So the next thing you have to know here is to identify the functional group in this compound. It's very easy. The functional group of the compound determines the chemical property of that compound. It's actually a very special group that distinguishes a particular compound from all other compounds, meaning that the functional group here in this compound is this double bond functional group. I believe you can see it here. And a double bonded compound should be called an alkene. Do you understand? A double bonded compound should be called what? An alkene. Now, next thing we have to do here, since we want to name this compound, we have to make sure that when we are naming, the functional group have a lower number as possible, meaning that if you observe, if we count from here to here and also counted from here to here, what number do you think the functional group will fall under? Now, please note this. Let me quickly explain something. I believe you can see that the functional group is between these two numbers. Now, I'm looking at it in this direction, this up part. So you can see that the functional group is between carbon 1 and also carbon 2. Now, the reason I'm doing all of these things is to make sure for you to, when you see other questions, you can actually solve them on your own. That's why I'm taking time to explain all of these things. So you can see that the functional group is between these 2 carbons, 1 and 2. Please note, the functional group should go to the carbon with the lower number, which is carbon 1. Do you understand? That's why I said that the functional group should have a lower number as possible. So for instance, we were to take this to be the normal way to count, you can see that it's going to be between 3 and 4. So which of the carbons do you think will get the functional group? We claim the functional group is going to be carbon 3. Do you understand? So please note this, that your functional group should have a lower number as possible when you're naming an organic compound. And what did I just say? Should have a lower number as possible. So definitely, do you think I can use this direction to count? No. We already have 3 and 4 and 1 and 2. So definitely, this will be out. Because we said that our functional group should have a lower number as possible. So it's going to be, we are going to count in this direction. Do you understand? And next, see that the functional group should fall under which of the carbon? Carbon 1. Because I've explained this already. If you're having 2 numbers, go to the lower number. So definitely this compound should be called bute 1. Why did I call it bute 1? Is an alkene. Do you understand? With a double bond. Alkene. So the next thing we do, we have to locate if we have any other substituent. And in the look of things, we have this substituent here. I can't call hydrogen a substituent. Why? Because all of these are HCs. What do I mean by HCs? They are called hydrocarbons. Do you understand? So I'm not really interested with the hydrogen here, because what I'm interested here in is all other things that we appear apart from hydrogen and carbon. Do you understand? So I saw CH3. CH3 basically is a special group. I've done this in one of my video lessons. And CH3 basically is an alkyl group, specifically called the methyl group. Do you understand? And it fell under carbon 3. So definitely this should be called 3-methyl bute 1-ene. So what becomes the answer to this question? Option B. It's actually very easy. Now note this, between numbers and letters you use dash. Do you understand? Between numbers and letters you use dash. You can see this is a letter, this is a number, that's just separating them. So that's how it works. So I believe that you understand how this concept works.
Yeah, come on.
The pets are some. Ah. Oh, something.
But in fact, I hold you on, but I've got now.
This program is supposed to be face to face throughout. It's supposed to be face to face throughout.
In the upper man more.
Hey.
Oh, I can't go.
More part of course, speed, he was going very fast, Sometimes network is still a big looking at it.
Oh, Rafa. I'm an I started. We are in an introduction. I mean, Adama. Yeah, Ubia in your time not national. Usher slides in the moment in Yama no because you will be one man. Already, the editor shared about you in the in this. Yeah, come back now. Yeah, you're wishing a grand grab when we be a baby. I'm a kind of book about to be the man, me, the same book. But it's a slide, man. You might think it's about the way you were there. You do not assume, but then you see into all be a young printer, printing about that national shumer.
Yeah, it's true.
I can't be absent. I tell you,
Okay, how were you for them?
I will use it.
Cape Kuswala.
This is Ambo campus one.
I'm not trying to put a doctor by face to face.
Oh, so I'm an what friend then. I'm an 11:30 then. Second aid moment I start. But look, I'm an what on your better, matter, all the work a day. Class will be more than on print. I say, more than on print. Not what I don't show. One of the one man, let's see that. So do now, yes, but you
also no. Oko speed do oko speed. I didn't see them know that you have a tire crowd. Anyway, then Marcano, you are going to print the slides and then maybe we learn from there.
A print a slide not national shuma. So when started I can never be
our area of friend the chemistry major and the physics.
May chemistry.
I'm a physics. Physics. I'm a physics major.
Physics mean be that. Physics mean be the only problem.
But physics is more mathematical and chemistry. Physics
science and again. Physics might be that me chemistry biology got me my physics mean the more I compare me chemistry physics. But me the more physics in the moon. I should put my hand to me and I
Which one? Physics, I mean, chemistry, are too complex. Physics is, it looks at least little bit calculation. The man, I don't know about chemistry. Well, chemistry, my guy, my all start to yeah, me chain, butane, pain, or whatever. But
yeah,
you have a talent. I do. Anyway, me should them I can go for them. When for you are going to pick it.
Obi am print the slide. Print the slide. That's all I say. Shoot, my doing that. But I can't get
Let us wait for the next year.
I'm a medium.
Mm.
Mebajo, has the lectures on the biology started? Hello? Hello? Ujavo? Biology lesson, Ashasiana. Hello? Ujavo, biology lesson, Ashasiana.